Okay, there we go. So we are live. Happy days. Minor tech issues, but nothing too big. Everybody, welcome to APEC. It is April 11th, 2026. I'm your moderator, Tim Ventura. I am really excited. We have some amazing conference presentations today. Thank you to everybody for joining us on this call, along with everybody watching us on YouTube, Twitch, X, LinkedIn, and Facebook. We are live streaming to multiple channels. Again, super exciting. So starting things out today, Dr. Thorsten Ludwig will be discussing his research into zero-point energy and the Casimir Effect. That is a tremendously important and popular area right now. Mikolaj Baczynski will be discussing vacuum pendulum testing with the beam balance, and he's going to be doing pendulum timing tests that produce a reproducible propulsive force. Bryan St. Clair is going to be discussing the evolutionary arc of his pulsed inertial engine devices, and that's kind of a past, present, and future. That was something that I've been urging him to discuss because he has done so much over such a long period of time on that. And Michelle Broyles is going to be giving us in-depth updates from the Shell-Woodward lab on her research into Woodward Effect propulsion. That is the MOX principle propulsion. She has done a tremendous, absolutely amazing amount of work, incredibly meticulous, detail-oriented. She worked with Jim Woodward for years before he passed, and she is still with the project pushing things forward. So again, I am really excited about today's presentation. Let me quickly apologize for the noise. I still do not have my studio set up. I should have that in place. One of the things that slowed me down there was I was just at Deep Tech Week 2026. I picked up photos of Eric Weinstein, Harold Sonny White, Dr. Charlie Bueller, Manelli Max Derek Shawnee, and of course, Mark Sokol. They all spoke and presented on emerging concepts in propulsion and energy. It was very exciting. I am anticipating that video will be available for that. When it is, I will let you guys know where it is. I also have photos up on my Flickr gallery. That was kind of my role there. Also, Mark Sokol is going to be going to the Panic NMR conference in Washington, D.C. in early May. I may be able to join him. It depends. I'm not entirely sure yet. That is related to the dynamic nuclear polarization Alzafon experiment that he's been working with. We also have the McMinnville UFO Festival coming up. I'm thinking about taking a bus down to Jared's lab and Isaiah Ritchie's. Isaiah is working on incredibly well-constructed Searle effect generator replications. And of course, Jared is building a lab for in-depth UAP sample and propulsion testing. So those are just a few of the projects that are currently going on. Again, super exciting. So today's event is on StreamYard. We are broadcasting through the Alt Propulsion YouTube channel. If you haven't subscribed yet, please subscribe now. You can ask questions using the live chat feature on the right-hand side of the page. We will try to get them over to our presenters depending on how fast things move and time constraints. You can also view conference replays, details, and speaker info on our website at altpropulsion.com. And if you haven't visited Alt Propulsion recently, I have been putting up story after story after story on past presentations, as well as topics that are within kind of our focused coverage area. So definitely check out altpropulsion.com. Okay, so let me get started. Number one, we are going to go right to Dr. Thorsten Ludwig. Again, he's going to be talking about zero-point energy and the Casimir Effect. This is an incredibly popular area right now. So I'm going to bring him in. Thorsten, welcome and thank you so much, sir.
Well, thank you very much, Tim, for inviting me to APEC. I've been watching and following it for quite some time. As I told you, alternative or new propulsion is one of my main topics, and I mainly got involved in energy because of looking for the energy for the propulsion. And and early on, I got into you want to say something more?
Well, I was going to say, so let me do this. I will take myself out of the screen. I was going to hand things over to you completely, sir, and then I would say take it away, and let me know. I will be here in the background if you need any help, sir.
Yeah, okay. Hello, everyone, to this talk on zero-point energy. So in my search for new propulsion as a physicist, I early on got involved into zero-point energy. It caught my interest, and as an experimentalist, I, over the years, more and more worked with the Casimir effect. So let me show you what I will talk about. So I will talk about zero-point energy, a little bit of the history. I know that has been said here before, but I want to say a few things on that topic. And then I go into the measurements of the Casimir force that other people have done, but mainly in this section what I have done. And also I want to make a few points on magnetism and zero-point energy and some outlook. So let's start with David Bohm. He said space is not empty, it's full, and we are in it, and everything, the universe is connected to this cosmic sea of energy. So this is like an artist view of the quantum fluctuations of the energy in space. So how it came along here, well, I'm working in Berlin, and in 1900, Max Planck, he offered the quantum mechanics, this early formula here, as a solution for black body radiation. And he always kind of wasn't sure if that's the right way, so he questioned that a lot, but somehow he felt forced to do this. Well, then came the photo effect, and so the quantization became more solid. And then 12 years later, he came up with this second formula, which already had this +1/2. And that is what we call the zero-point energy. He didn't call it that at that point. In 1913, Einstein and his assistant Stern at that point, he later became famous for his own research, but they published a paper, and it was Einstein and Stern who came up with this name, zero-point energy, in that paper. Or in German, Nullpunktenergie. It was a German paper. So then it went on here, so we're standing actually on shoulders of giants here. Nernst, he kind of thought more about this. First, the zero-point energy was only on simple systems. Nernst expanded it to space. And then when Heisenberg and Bohr came along, and the uncertainty principle, that is what explains the zero-point energy. But historically, it came much later, and it didn't start there. So the uncertainty principle is very much connected to this wave-particle duality. So sometimes matter or energy behaves as a wave, as frequency, and sometimes it behaves like matter in the sense of balls or billiard balls. So, I think right now we have more tendency to look at matter from this billiard point way, but in reality, the frequency is also very much there. So not only there is an uncertainty between a position and inertia or momentum, there's also this uncertainty between other pairs, and energy and time is one important pair for us here. So, and you can explain the 0-point energy from that point, but it enables also quantum tunneling effects and has to do with the probabilistic nature in quantum mechanics. So I know a few months back there was someone who expanded the theory and the development from this point way to today, but I'm not taking that route. I'm only saying these people from the history because Casimir here came up with the Casimir effect. So Schwinger, Feynman, Tomonaga, and Lamb, they expanded it more and more into space itself and developed the quantum field theory, also the relativistic Dirac equation came here. So, but for me in this work here, 1948 is important when Hendrik Casimir here in his, as when he discovered this, and this is later at a conference where I actually met him. So I really do like this this picture, a very humble, nice man. There was a conference with 300 people working for years on the Casimir effect. They celebrated 50 years with him on that day, and he gave a speech. It was quite impressive. So here also he said how he came about doing it. So he worked with colloidal suspensions at Philips Labs in 1947, and back then they made cathode ray tubes, they made lightning bulbs and other things where they needed these suspensions. And so he worked on the physics of that and found out that it's related to van der Waals forces. And somehow he was a friend, I think even a student from Niels Bohr. So when they met again, he told what he was doing, and Niels Bohr mumbled something like, must have something to do with 0-point energy. So he picked that up and it became a great influence. And he understood things better, but also kept thinking theoretically, and then came up with this idea with a simple configuration, 2 metal plates close together. And what that leads to is here, the red is the metal plates. And the lines you see here are the frequency. So some vibrations of space or some quantum fluctuations, they exist outside. So especially the long wavelength, they can exist outside, and inside it's more and more restricted. So there is less quantum fluctuations. So you have a force pushing these together. Now, I'd like to mention at this point that even Casimir admits you can think this differently. You can explain it differently, but this is one common way of understanding this phenomena. And you see the force here. So the Casimir force is so important because it converts the quantum fluctuations and this whole idea into a measurable force. So if you like to do calculations in this arena or understand it more deeply, I recommend this book here. And also here the author explains, not a physicist, engineer, he explains very clearly that the Casimir force and the van der Waals force are basically the same thing, but the just different extremes. The van der Waals force is with dielectrics, and the so-called dancing charges, and the Casimir effect here with metals, and especially with a limited light speed. Now, an ideal metal can't have any difference in charge. That's kind of the definition of an ideal metal. But still, the limited light speed makes an effect, and that regime is then called the Casimir effect. But actually, if you go deeper, calculations, everything, it's the same thing as a van der Waals force. Now, I always like if nature is using it. So here you see in 2005, they found out how the gecko is hanging from the ceiling, even if it's glass or it's not hooks or anything, and they can be kilos heavy. They have a lot of small hairs, which are all flat at the end. And so they use this stiction resulting from the Casimir and van der Waals force to actually hang from the ceiling. So if it can be used by nature, I hope we can also make use of it. So now comes the experimental side. So there was some a guy named Sparney who made an experiment in the 1950s with 100% error. I mean, that's only factor 2 for the physicists, not that bad. So he measured it, but it took then another 50 years till Lamoureux came about in 1998, and he started this modern type of experiments. These are Mohideen and Maclay and Descartes are some other names. Descartes is the one who came up with this setup. So, and the Mohideen setup I will also explain in more detail. So they are all using modern nano positioning and techniques to measure very small forces, pico and femto Newton. So Descartes, that's his setup here. It's extremely nice because you have the optical fiber here, which actually allows you to measure the distance here. We will see later on that that's an extremely helpful feature that most other setups don't have. Then you have this sphere here. Now, I don't know any experimentalist who actually realized a flat configuration, meaning two flat pieces of metal and measuring the Casimir force. Everybody who was actually successful used a sphere. It has a great advantage that if you come close here in the range of 100 nanometers, the sphere usually is like 200 micrometer. So if you come very close, you don't have to position the sphere. It always has the smallest distance somewhere, and it doesn't really matter where, because actually looking and in 100 nanometers, you can't see anything anymore. So with micrometers that you can see. And yes, there are techniques of like atomic force microscope, but they are not, you cannot measure for positioning, you need optics, or in this case here, there's the interferometer and you can measure the distance. So this is a micro machined device, and it's like a little balance here, and very nice setup. So this is how it actually looked. Here is the ball, here is the flat area, the scale, and this all is extremely important. It needs to be super rigid, optical precision, positioning, because everything has to be super rigid and solid, so you can actually have this nanometer positioning and then measure the forces and the distances. So this is a setup that Mohideen kind of originated. And for those of you who are not so familiar with physics equipment, this is a so-called atomic force microscope setup. So in the atomic force microscope, you will have a needle-like point here, and you will scrape this over your surface and then come up with a picture. But this cantilever, it kind of bends here up and down depending on the force here. And with a laser that is reflected from the tip of the cantilever and detected by the photodiodes here, you can kind of measure the bending. And with this, you can, every big lab has at least one atomic force microscope, very handy tool to look at small surfaces, surface structures. And biology, you can do extremely many things with it, but here we use it to measure small forces. So this is like in my lab how this will then actually look like. You have the laser here, you have your detector and the optics for the detector here on this side. You have the positioning. Here, this very little tiny area, that's the holder for the even smaller ball, which you cannot see on this picture. And this is like the other side, the flat surface, and this yellow thing here is a piezo actuator. It's a crystal, or it's a ceramic. It's a ceramic where if you put some voltage and a very stable voltage, you can do nano positioning. It's a little bit of a long one because we need to actually pull at something between 15 and 30 micrometers. That's important because actually what happens is that you come closer and closer, and then comes the point where the force accelerates so much that it sticks, and then you need to kind of retrace quite a bit to actually pull it off again. So that's a common problem. So this is here where the point, you see how closer and closer it kind of really gets, it's very steep here. So here you see the Casimir force in piconewton, and here is the distance. So 300 nanometers, 200 nanometers, 100 nanometers, and then somewhere between 30 and 50 nanometers, the ball will just stick. So obviously you don't want that because it kind of disturbs the measurement. So now this is a list of things that in the experimental arena, the Casimir effect is well studied, but there's a roughness correction, a temperature correction, then the finite reflectivity of metals, the plasma frequency is very important, real materials, and then the theoretical people, they discuss different methods of how to calculate this, especially between approximation and optical and bulk methods. These are the topics. And this is a nice graph where you see here just around 1 micrometer, this correction factor of only temperature and the plasma frequency is about 1. If you are between 1 and 10 micrometers, you more and more the thermal photons play a bigger and bigger role. Unfortunately, in this area, the energy gets less and less. So you saw at the Mohideen, it's already pretty flat there. So on this side, the correction factor goes down because the metals become more and more transparent. So if you go to X-rays and if you go to gamma rays, they just fly through. And so the Casimir effect doesn't work anymore. And that's why this correction factor goes down here. Here is a lot more energy. So this is the more interesting area. But of course, if you go below 100 nanometers, the roughness of the material really gets in the way, which is usually at least 30 nanometers. So if you are interested in that, you can still read this paper here, can remember my name and a few keywords, and at Science Direct you can pull that and you can read a lot more on my early work. At this point, before we are going more into experiments, I like to point out that there's also a very deep connection between zero-point energy and magnetism. And for energy and propulsion, that's highly interesting. I can't really go into these Feynman diagrams, and this is like calculating the magnetic moment. And theoretically, that's very important from the interaction with the quantum fluctuations. So, and I also have a paper here where you can read on that. So, Kohler and my name and this, you can read more on that. So now I already showed this. So here is a laser. So I have two of these setups. I do two different experiments at this point in time. So this is a little bit dismantled, you will see. So you see a lot of optical positioning, and really one of the most difficult things in this whole Casimir work is to do the alignment of the laser, this optical measurement. And you can't see here. Here somewhere is a bent cantilever with a ball at some angle that you don't know. So it's you need a lot of time and patience. So the whole setup looks then like this. You have the computer here to collect data and to run the experiment. This here makes the voltage for the 0 to 150 volt for the piezo actuator. There is a control for the laser and control for the optical for the photodiodes. We use a 4-quadrant one, so you can also measure the bending of the cantilever and not just the bending, also the twist. Yeah, so it's quite a simple setup. It's decoupled here for against acoustic and vibrations. So it's basically a breadboard and some optical equipment and a lot of putting everything at the right place and adjusting all these knobs till it finally works. So here you see the bottom is like the flat. I use usually optical mirrors because they come in the right size and shape and flatness. And this is the holder for the cantilever, which is basically, this all I built myself. The rest are bought components, and the cantilever is coming from the AFM sort of suppliers. So here you see where the laser is actually hitting the cantilever, and here you see the piezo. And this is a USB microscope, because you need to bring the flat part within a few micrometers of the ball, of the sphere, and then you can work with the piezo, which has like something between 0 and 30 micrometer positioning. So it's very important to use these optical microscopes to pre-position everything. So now here we see that it actually works. You have to look at this graph here. This is ramping the voltage. So up to here 60, we don't see the peak. It's probably 60 or 70 volts and then down. So now here is the main response. So what do we see? So here comes the point. Well, remember we had some voltage, then it drops down here. So here is this 0 volt position. So then we apply a voltage and we kind of come closer and closer. So if we are at the right position, we see this curve of the force that is getting high, more and more and more. And then comes this point up here. That's where actually the ball kind of sticks to the surface. Now, that's very close here to the point of the highest voltage. Yeah, I did that on purpose. Because then once you hit it, you see you get closer and closer. You kind of push the ball. You push it a bit. And then here comes the point where you start retracing. And so here you see the stiction. It kind of takes a long time till the force of the cantilever is strong enough to pull the ball off the surface. And then the force drops dramatically down. And here is, so this is only to see that everything is working. For my experiment, I don't want this because this is kind of disturbing everything. It's not good. It's not good for the setup. I try to avoid that. So when I know everything is working, this is what I work with. I do my measurement and then I stop before the ball hits it and so forth. But it's temperature dependent and so forth. And it's on the long term, you again and again run into this catching in and pulling off. But sometimes if you know what you're doing, you can make a lot of measurements. So now I explained a lot about the setup and how it works. Now I want to show two experiments that I'm doing at the moment. So now we have to jump Casimir Effect and propulsion. Now there's these names. Jordan McClay, he had a paper, I think in 2004-05, which is very interesting. Friend of mine, Fabrizio Pinto, he published on that on Casimir Effect and propulsion. We know that Harold Sonny White is working on it. There's a very good interview here on APEC, and here Robert DiBiase, he's also working on that, and he talked in October last year. So I put this name last, and because I'm working together with Robert, with Bob, and so here's Fabrizio Pinto and his idea and his company, Interstellar Technologies. So now he has moved on a bit. Here is the Jordan McClay paper and some reference to that. So now we come, and here I will only briefly talk about this. If you're interested in this, you should. Bob talked 1 hour about this in October. So, but anyhow, so the basic idea here is it's called a Casimir wedge. So you have kind of this sawtooth on one side, and the clue is here, it's only half-sided metallized. So one side is dielectric, one side is metal. And so that's the basic idea. So now I'm working together with Bob on this for quite some time. And so I show 3 different phases. One phase where I actually used the atomic force sort of Casimir measurement was this phase here. And in order to measure the force on the corrugated surface, it had to be on the ball, because only the ball can be measured. And not the flat cannot be measured. So I had to find a way to actually put this structure onto the metal sphere. So here's how the setup then worked. We did different configuration, but one main configuration was like this, that you come with a flat from the side, and then you want to measure the so-called lateral force, so the up and down force, not this force. It's difficult but doable, and we came up with some interesting results, encouraging results, and this is how that setup looked like. So coming with a mirror from the side to this setup, that was very challenging, but I did over 1,000 runs with this, with different balls. I think I made 5 or 6 different balls like that. So how did I make that? I used diffraction gratings usually from Tor Labs. So here you have that refraction grating, and here is a holder and the ball. You can't really see it. Here you see again the microscope. So positioning is extremely important. The grating has to be heated. I first heated the ball, but for this configuration, I needed to heat because the positioning here is to put the structure on the side is so difficult that I needed so much time that I needed to heat the grating. So here is temperature controls and so forth. So I stamped, actually I stamped the ball into the grating. And here is the AFM picture that it actually did work. So now then we moved on. We want to make larger effects, and so we came up with Bob came up with the idea we make these mirror grating combos. So then we just have to take the whole grating, put a mirror on top, and this is the Tor Lab gratings. We now then use square inch. This is how I half metallize the grating. So I take off the normal coating from the grating, position it in the right way, and then put aluminum on top from a steep angle, so it only hits one side of the structure. This is the mirror we use and the optical properties, which are important for us, especially here. That's why we use UV enhanced coatings, because here is more energy than here. And the fantastic thing is these combos, if you put them on a scale and you put them grading up or grading down, you measure a weight difference with these sub-microgram or sub-milligram scales. So, and that was very encouraging. So we went on, and here you see Robert DiBiase in his lab and doing the same thing. Well, actually, he did it first, and I then replicated it, and it's working. So it's encouraging. So then we went on to put these combos on floating devices. There's water here. It's a top view, so we see it's turning, and this is something that Bob did. And because it's interesting and encouraging, I replicated it. This is one of 3 or 4 setups. Here you see the camera, the water, the dish here, and the computer to track this. So nowadays, it's a lot to say about this, but I just take 1 frame per second. So I'm using kind of a prompt-like program, which takes 1 frame per second. Then we analyze it with a program called Tracker. So you can then convert the video into angle and velocity. And this is like one of the interesting runs. And here is another. You see a different dish. I thought it's interesting to have a structure so you always know how it's turning. But actually the white one works better with the tracker. So it's also encouraging. So now time moves on, and now I want to go to my second experiment. And so we go back to the quantum fluctuations and the plane Casimir setup. So as many people know, this is like also in my paper, but here I presented the yield from the Casimir effect. So now if you think, okay, I just use a normal Casimir effect, this is what you get. You get like 1 micrometer, square micrometer is what I get in my experiments, and 100 nanometer distance. And then you have something like 10 to the power minus 13 joules, which is not much. So if we go to larger areas like square meter, square kilometer, of course, how to do it, I don't know. But if it's 100 nanometers doable, so you get like half a joule. Also not much. If you combine it with smaller distances, like 1 nanometer is already like the distance of 2 atoms. And here the femtometer is like nuclear, like a proton distance to another proton in a helium or something like that, so that's very small distance. So if you could find a way of going there, then you have more juice, but it's very difficult to think of that. But I also have an interest in consciousness research, because my main interest is the Indian Vimana, and they were thought controlled. So I also have an interest in mind-matter interactions. And in that area, there is the PEER lab, the Princeton Engineering Anomaly Research, and they made over 3 million experiments with random processes and found that there is a distinct, they found that there is a 1.1%, so 1 per mil influence in average by normal people on a random process. So my idea that I proposed 15 years ago on a space conference is that to test if we can use that to make a difference in the 0-point energy. Because if we could make 1.1% influence on the Casimir forces, on the quantum fluctuations, it will be a lot of energy. So if we do the calculations, we come up not with minus 13, no, we come up with 10 to the power 63 joules per cubic meter, so an enormous amount. So if we find even a small way of doing it, a very inefficient way, still it would do quite a difference. So one of the Casimir setups that I've shown, I'm using to test this, because after talking about it and looking for funding for 15 years, I just thought, the heck with it. I'm just financing it myself. So I took what I had and bought a few things and built another. If you know how to do it, it's not that difficult. So I built another Casimir setup. And the setup is ready for 2 years now, but to do consciousness research is even more difficult than lateral force. You have to work with people, you need the human interface, you need a protocol, and it's challenging, but I'm on it. And very curious to see what comes out. I have experience in this. I published a paper with Bill Tiller on some other mental force experiment that I worked on for years. So one way of doing it would be, I don't want to go into it, how to do it, but basically Bill Tiller used a machine to to program the intention into an electronic device, and he used that to enhance the force, and that could be done here too. So the setup is ready, and I'm doing trial runs and fighting with the remote control and stability of some things, but I'm working, I'm getting there. So now I want to use the rest of the time to show a few other things that I'm doing. So I'm working for many years on the Kohler generator, because that device was tested in the 1940s at our university in Berlin, and a very famous professor there, and one from Munich, the well-known Schumann, they tested it and they were impressed by this Kohler device. The British intelligence brought Kohler over to Britain, and under severe surveillance, he rebuilt his apparatus and was successful. But it was so stressful, he died after that. But unfortunately, the report on that, here's the intelligence report declassified, and here is the Kohler file from the UK archives. So there's a lot of documents. Reading them is always, oh no, if administration people write letters on science, it's tough. But anyhow, there is a few useful information in this file, but I don't have the time to go into it. So it's actually a circle of 6, a hexagon of 6 permanent magnets, where there is a coil wound around them. Kohler built it in this way, so there's no input power and only output power, because even back then people thought it is more impressive. So we rebuilt it, and like I said before, there is a very deep connection between zero-point energy and magnetism as such. So I do think magnetic apparatus like the one from Kohler is a good starting point for looking for an energy device. And so the spin and the interaction with the radiation field, with the quantum fluctuations, they actually change the magnetic moment of the electron, and that can be measured. If you measure it very precisely, you come up with this number here, and from the Dirac equation you get the number 2, and so the rest here is definitely from the radiation field. There's no doubt about it. And that can be calculated. And I still work with Tom Vallone on how to explain the full magnetism with zero-point energy, but I must admit that theoretically we haven't built that bridge yet. So, and the Kohler device is also not so easy to work with. It needs a lot of tuning because there's some self-resonance in there, and but we have done it a few times and got it running, and energy came out, and so this connection to the zero-point energy, I think, would be I also tried with magnetic force microscopy and other ways of looking into if I can actually trace what's happening there, but it's not complete yet. So I have two Kohler papers out where you can read a lot more detail on what I did and how I did it and so forth. So this is another generator which came to us. It's a chrome ray generator. Also, this is a combination of a generator and a motor. And chrome ray had some ideas and very much connected. He thought magnetism is related to gravity, and that inspired him to build this this machine. Quite interesting. Yeah, published here in Extraordinary Science and Technology. There is this article. Then someone, a big European airplane builder, has built this magnetic motor, and somehow, as things go, it ended up with us. So we have to see what it's doing and getting it to work. And then maybe the last thing I will say is I work with the neutrino group here, and they claim that the energy from their foil-like, looks like carbon paper or metallized carbon paper, but it's actually the main thing is graphene, and it's multi-layer graphene, and it's quite an interesting, a very interesting material, which I'm not prepared here to give a full lecture on that. So I'm just showing you that I work on this. There is this Professor Thibodeau who built this device here. He so the neutrino group wants to bring it out into the industry, but he really figured out how to measure it. He has this integrated circuit, which is many of these graphene cells. So he did a wonderful full job in measuring it, and and was really surprised that everybody's so interested in his device, and all the people asking the question, is it violating the second law of thermodynamics? And he said, oh, I'm just building an energy device. What are you asking these questions? So here the neutrino group, like I said, they want to build this, but working with groups from the industry, it's not so, is a different difficulty, but I don't want to go into it. But we went to India. We met the Ministry for Electronics and Information Technology, and the people were very interested. Met like kind of a sub-director, like a sub-secretary of that ministry, and they were very interested in doing something, hosting it, and it was wonderful to see that people there are very open for innovative ideas. So basically, I'm finished, but I want to show you a few pictures of the Vimanas, the flying palaces, or the flying in Indian mythology, the people who lived in the Golden Age, which is like 5,000 years ago to 3,000 years ago, when there was peace, there was plenty, there was gold, there were palaces, there were peace. They had these, according to the history in India, they had the Vimanas, which they can be as big as a flying palace, but they can be as small as this. So I hope we we will be able to build something like this. See crystals, you see two people sitting there, and so which is kind of with a smart new propulsion system, picking up your thoughts. So you think where you want to go, and you start slow, looking at the surroundings. And when you think, oh, it's time to be there, boom, you're there. So with this, I end.
Thorsten, that is awesome. And so you have, I'm going to leave this slide up for a minute. You have your contact info on this. You have your website, thorstenludwig.de. That is in Germany. Actually, I have been following Neutrino Energy Group. I've been talking to them as well. It's very exciting. I didn't realize you were working with them. And then I've been into consciousness research. So I'm like right there with you, my friend. Thank you so much for presenting today. And one of the things that I hope to do is I'm going to try and create some breakout sessions. I've been doing that more lately. And so I use transcripts, load them into AI, and then I put them with the videos. And what we're trying to do is just get this information out there to the widest possible audience. So
I'd like to mention one thing. We're very interested in open source. You know, we publish everything. We want people to pick it up and work with us and bring things forward.
Yeah. Well, it's exciting. There is so much happening right now. And the Casimir Effect. I mean, thank you so much for presenting on that as well. I think Sonny White really catapulted that into the spotlight recently, right? But like Dr. Garrett Modell has been working with that. You're working with that. Dr. Fabrizio Pinto. I mean, he has been working with that for 20-something years. Yep. So there are lots and lots of folks who have had their hand in that pie, so to speak. And from what I can see, it's producing results. It's absolutely remarkable. Okay, well, so we are at 12:57. So Thorsten, let me thank you one more time. I'm going to take your slideshow down. And so you're happy to, I mean, you're welcome to stay in the studio if you like. I do bring people in. I'll bring them back in occasionally. But let me bring everybody in right now. And in true APEC form, guys, let's put our hands together and give Dr. Thorsten Ludwig an enormous applause. Thank you so much. And do you guys have any questions?
It was a pleasure.
I have a question, if I may. Thorsten, in your opinion, what is the energy density of the vacuum?
Yeah, that's a good question.
Sorry about that.
Calculate it. You see, I'm a down to earth guy. Okay, so I, like you see, I do measurements and things, and well, all I can say is that the Casimir effect works according to theory, you know. So, and from the quantum theories, the density should be high. You know,
it is 1 to the 120. That's what you say.
Yeah, so I think it's high, you know, but the real question is how to use it, you know, and so I think Casimir was quite brilliant in coming up with this super simple setup. Actually, that's how he came about. He thought, what is the most simple thing, you know, and he needed 2 states. So he said, okay, if I need 2 states, why not do this with the two metal plates?
Thank you.
So from the theory, you can calculate the forces, and they match up extremely good, you know. So, but is it high or low? I mean, that's like asking a fish what the pressure of the water is, you know. It's only if you kind of feel it. You know, if you kind of change the height or something, you know, only if you feel it, you can actually do something with it. Otherwise, it's just all around us.
I should ask, Joel, did you have a question?
Yeah, I have a question, and Dr. Thorsten, that was an awesome presentation. Tim already told me a lot about you, and I wanted to get in contact with you before, as I'm from Hanover, Germany. So I really should get in contact and visit you. So my question was, are there experiments that actually use parallel plates? Because I understand that the sphere is much more practical, and I also understand the sawtooth experiment. It's very interesting. But there are certain theories which actually have a structured space, like Heim's theory or Curtis Horn's UQFT theory. And in those kind of theories, that geometry of the sphere, for example, is theoretically suggestive, right? A sphere plane setup does not impose a uniform boundary condition. It imposes a smooth spatial gradient of constraint, and that would maybe have a different influence than just two parallel plates. So is there actually a parallel plate baseline experiment to which you can compare different shapes?
Well, first of all, from an experimental point of view, you lose 1 order of magnitude in the formula. And if you are at micrometer, that's a lot of orders of magnitude, okay? So, but yes, I know in Italy for years, they had a very well-funded Uno Frio, I think is the guy on my list. He tried the flat geometry, but I never saw a paper from them where they actually succeeded. But they at least worked hard and for years and well-funded at a university level arrangement or government lab. They really worked on that.
That's awesome, but you said they didn't succeed, so there is no base.
I don't know everything. I mean, I haven't. They might have succeeded.
Maybe they have latest results
about it, but
yeah, very interesting.
Maybe we have to follow it up and see how far they got. You know,
I really also like your consciousness angle on the whole thing and your description of the Vimana in the end. It reminded me on a description of the so-called projector drive, which is a theory by Ilobrand von Ludwiger based on Heim's theory. And we should talk more about it.
He was also on that line, no? He had a few mental dimensions.
Yes.
Which I really like the Heim theory, so we should get together and discuss.
Yeah. Awesome. We will. I've got your contact. I will contact you.
Yeah, contact me. I pass by Hanover frequently, you know.
Wonderful.
Oh, yeah.
Well, guys,
if you want, we can also meet. Very nice.
We're at the top of the hour. So if it's okay, I want to go to Mikolaj. And again, Thorsten, thank you very much. Thank you very much. And I would love to have you back in the future if you have more that you want to present on as well. But for right now, let me take everybody out except for Mikolaj. Mikolaj, welcome, sir. So you are going to be talking about vacuum pendulum experiments that produce a propulsive force. And I think, let me see, you have a screen share to do as well, right? But in your
I think if you can play the video would be best because I have a presentation.
Do you want to try and do that? Do you want to try?
I don't know. I cannot do this because I'm not allowed to download. I give you. Hold on. I can post the link. I sent it to you in the email, but just in case.
Okay. So for APEC, April 11th. So let me go to the MP4. Let me see if I can.
Because we did that before, and that worked better than
Okay. So let me do this. I am going to share screen, and let me see. I've got too many windows up here. There we go. Okay, so this is the Google Drive. So let me play this, and we will cross our fingers and see if this works okay.
I hope it does. The possibility of building a propeller that would work in a vacuum. Today, I'll expand on the idea of exchanging momentum with the vacuum by adding pendulum tests and summarizing my research. I'm looking for collaboration on every level, and given the extraordinary claim, one must remain strongly skeptical. Let's take a closer look at the thought experiment. Consider a vacuum fluctuation as a pair of particles with opposite charges moving in the opposite directions. In non-uniform magnetic field, particles with opposite charges are deflected with different forces, and as a result, at the end of a fluctuation, momentum is transferred between magnetic field and the vacuum. You can look at here, the Fa is larger than Fb. We have to notice one thing, that accelerating the magnets will result in transferring momentum into the vacuum. And we can estimate the particle velocity based on the vacuum energy, and the distance traveled is driven by the uncertainty principle. Current physics disagrees with my assumptions, and the main violations are as follows. Vacuum energy is not a reservoir that you can tap locally without modifying space-time boundary conditions, and Lorentz invariance demands that the energy is isotropic. In quantum field theory, vacuum stress energy tensor in a static magnetic field is symmetric, and momentum density remains zero. Experiments that do show vacuum momentum transfers are fundamentally different from static magnetic gradients, and they involve time-dependent boundaries, moving mirrors, and radiation emission. And the big question is how the experimental physics could have missed an effect that contradicts Lorentz invariance and produces 200 micronewtons of force. Current physics versus new vacuum. Vacuum is not an elastic medium according to current theories, and static anisotropy alone is insufficient. We need time dependence, a boundary, or external gradient. What if the vacuum is an elastic medium? Then we could break vacuum isotropy, and in such case, the probability that the experiments I've done so far prove the possibility of building a vacuum propeller would be quite high. Given the current state of theoretical physics, experiments are the way to go. Here is a link to a recent paper hinting that the virtual particles are real transient particles. How to estimate the quantum force? Quantum force depends on gradient of the magnetic field, average x component of particle velocity, and vacuum energy density. Given the vacuum energy, quantum force can be obtained based on uncertainty principle and the Broglie wavelength. I'm not going to go over these equations, but the final answer is as follows. Thrust force depends on field geometry. Since we are considering the y component of the field gradient, as shown here and here, given the same strength of magnets, the two-base magnet configuration may result in higher quantum force than the three-base magnet one. The quickest and roughest estimation of the quantum force could be as follows. To estimate the total thrust force, QF, we can define the effective volume VE. Such volume has the same magnetic moment at every point. So in that case, integration is reduced to summation, and the n is the number of fluctuations in the effective volume. So based on the experiments, the following values were used in calculations. The effective volume was set to 212 cubic centimeters, and BA was roughly about 1 Tesla. We can estimate the quantum force using field modeling. We integrate over the volume. For every x on the grid, we sum up values along the y-axis. And there are two methods. The delta y method. In that method, y points and delta y are based on uncertainty principle given the vacuum energy density. In delta by method, with delta by being the difference of by between adjacent points along the y-axis. Thus, at a given point, the quantum force can be obtained as follows for delta y and for delta by. Different methods, different results. What vacuum energy density is required to achieve a given quantum force? And let's compare the three methods. For the effective volume method, we get the lowest energy required. For the delta by method, we get the highest. If we compare the delta by method with delta y method, we see that for the delta y method, we get a quantum force 100 times bigger compared to the delta by method. I have the following questions. Is the effective volume overestimated? Is the delta by method underestimated, or does it need a tighter grid? However, the final question has to be, is any of these methods valid? Let's look at vacuum energies. Minimum values required for quantum foam to contain particles with mass. I'll pick 3 values, 10 to the minus 9, 10 to 3, 10 to 26. 10 to minus 9 gives us a pair of axion-like particles with the rest mass of 10 to the minus 3 electron volts. So nobody has ever seen an axion. We'll see. For the electron neutrino, we have a mass of 0.8 electron volts, and the energy is 10 to 3. For the electron-positron pair, with the rest mass of 0.5 mega electron volts, we have 10 to the 26. As fun exercise, I compared the repelling force between the magnets in the experiments to Casimir effect. So given 100 newtons and the effective area of 283 centimeters squared, I get 10 to the 4th. So that would correspond to the 10 nanometer distance between the plates in the Casimir effect. I have to make sure that it is clear that I don't think that bringing the magnets with the same poles closer together creates the Casimir effect. So looking at the values that support the results from the experiments, we have 10 to the 21st, which is fairly much lower than the energy required to create the electron-positron pair. But for the modeling results, we have values of quantum vacuum required much higher than the value required to produce electron-positron pairs. This value is high, however, is much lower than 10 to the 120 that results from the quantum field theory. But I don't really know what to think of these values and how to interpret them. Let's look at pendulum tests versus other tests. Beam balance tests, if you look at the results, they are very noisy. Torsion balance, the results are convincing. However, torsion balance is very sensitive to the interactions with the Earth's magnetic field. That's why setup L and setup R in these results had very strong negative bias. For pendulum, modeling enables estimation of the value of the quantum force, and when the direction of the QF is opposite to the motion of the pendulum, we are transferring energy or momentum into the vacuum, thus enhancing the effect. Let's take a look at the details of pendulum experiments, starting with gravity and friction. The horizontal component of Bob's gravity force, mg, determines the minimum value of QF that can be detected. And looking at the friction and resistance, we can use beam crossing times to estimate the friction. So the values that we use, the length of the arm was 1.5 meter, the Bob's weight was 130 grams, the initial swing was 0.3 degrees. That gives us value of 3,000 micronewtons for the force of gravity. The smaller the x, the more significant influence of friction and mechanical errors. And based on the beam balance of experiments, the quantum force is on the order of 200 micronewtons. So if we compare 200 to 3,000, that's a reasonable ratio. What is the influence of the Earth's magnetic field? 3 forces acting on a magnet due to the Earth's magnetic field are as follows. Vertical torque, force aligning the magnet in the vertical direction. Directional torque, force aligning the magnet in the north-south direction, the compass force. This force is absorbed by the pendulum structure and can be minimized by aligning the pendulum swing north-south. And the third force is the force pulling the magnet towards the Earth's pole, and it is 0 for all practical purposes because we can assume that the Earth's magnetic field to be uniform. So in conclusion, only the force related to the vertical angle, the dip angle, is of significance, and other forces are either absorbed by the structure or have very little impact on the swing times. Taking a closer look at vertical angle details. The force acting on the pendulum is proportional to the sine of dip angle plus swing, and values at the test location were as follows. Dip angle of the Earth's magnetic field, 69 degrees, strength of the Earth's magnetic field, 53.6 microteslas, and the maximum swing angle, 0.3 degrees. This picture shows how the forces from the magnets translate into the forces on the pendulum. So from this base magnet this way, and from the single magnet, force acting this way. If we flip the single magnet, the direction of the force would flip. So if you look at the direction of the quantum force versus the direction of the dip angle force, we see that for configurations as shown here, the direction of the quantum force is opposite to the direction of the force due to a single magnet. So the magnet configurations opposite to the ones shown above result in positive bias. That is, the direction of the force from the single magnet is the same as the direction of the quantum force. Here is how I measure swing times. Using ratios rather than direct values help to shield the errors due to sensor variations. And 2 microseconds is the minimum accuracy of sensor and hardware and software. So let's look how the measurement is done. We start here and we're swinging from the out zone to the in zone. We're passing the S1 sensor, nothing happens. We're getting to the S2 sensor, we record this value, we're swinging out to the in zone, coming back, and that gives us the in time. Moving back to the out zone, we hit the S1 sensor, going out and coming back, we get the out time. And the quantum force is determined via comparison between the NS and NS QFN configurations. So we have the NS configuration, we measure the ratio both in to out, and then we switch by flipping the single magnet to the NS QFN configuration, and we measure the values of the ratio between in to out, and we subtract the values. And based on the value of the subtraction, we see what the quantum force would be. And the value is determined based on modeling. Estimating the value of QF. Euler's energy time evolution method was used in simulations with the following steps. Model a single swing, use final potential energy of n- swing as the input to swing n, and keep n less than 20. Otherwise, the simulated swing period doesn't change much and there is little correspondence with the experiment. The time resolution was set to 10 microseconds, and that was based on IQR from the experiments. So if the quantum force exists, the following is to be expected. The NT to OUT ratio for the NSQFN is expected to be higher than the ratio for the NS configuration. And the opposite is for the SNQFOut configuration. The ratio of NT to OUT for the SNQFOut is expected to be lower than the ratio for the SN configuration. And that's what we see on the plot. This line represents simulation of non-magnetic wave, and the green line is the results from the corresponding experiments. So the force is determined based on the difference in these ratios, and that difference is linearized because I measured only 2 points, and the error introduced by linearization is way smaller than the error due to mechanical differences and noise and stuff like that. So it's all okay. Let's look at the test results. You see that for most of the configurations, these results are negative. And the main reason for that is that I used fairly strict pass criteria. and they're as follows. Both NS and SN magnet-based configurations are in agreement with the corresponding simulations, and the difference between in-T and out-T ratio must exceed the standard deviations, or IQR, as I used IQR, more than 5 times. So my conclusion would be that based on the modeling, the value of QF is on the order of 200 micronewtons, and the value of 200 micronewtons agrees with 200 micronewtons indicated by the beam balance test here. So probability that such correlation is random is roughly about 0.1 to 0.8%. Here are the plots based on the tests. We can see that this is NS configuration versus QFN, and this is SN versus QF out. You see there is some variation between the tests, so that's why my requirement that these variations would have to be at least 5 times smaller than the distance between them, and this is satisfied here. Let's look at bad news. There's no free lunch, and let's look at the effects of moving the assembly. So we have here the assembly perfectly balanced, and let's see what happens if we move this to the outside by 3 millimeters or to the inside by 3 millimeters. And you see that the difference between the middle and 3 out or 3 in is huge. So the assuming linearization of the effect, the minimum placement accuracy between the tests used to determine quantum force is required to be better or equal than 30 micrometers. That's huge. So let's consider the effects of changing the initial swing. The effects of changing the initial swing between 7 millimeters, which was standard, versus 9, and 7 millimeters versus 5 millimeters, we can see that there's a huge difference between those two. The 7 to 9, not that great, although significant, but 7 to 5, huge. So we say that initial placement of 5 millimeters is too small because the mechanical artifacts of the pendulum contribute too much noise. And assuming linearization of the effect, the minimum accuracy of the start swing is required to be better or equal to 250 micronewton meters, so which is not that bad. So let's look at yet another surprise. Oxygen paramagnetism, forces due to the attraction of oxygen molecules. If we look at the simulation here, you see that these molecules are attracted to magnets, and the results, magnets are shifted one way or the other. So based on the configuration, we have a different results. So for the QF in, we have the pull to the left, and for the QF out configuration, we have a pull to the right. And we can see here that there is also thermal noise, but for thermal noise, the results are negligible. Okay, so force on the magnets due to the oxygen paramagnetisms is opposite to the quantum force, if we can see here. So, but one note, compared to the mechanical noise and positioning inaccuracy, the forces due to the oxygen paramagnetism could not be properly accounted for. But they're very small and in the order of 1 to 4 micronewtons. Mitigating errors due to assembly placement. The difference in position of the magnet assembly between tests is the biggest source of errors. Pendulum's bob is a V-shaped base where the magnet assembly is positioned. 2 sides of the base were used in testing. Position blocker was used to ensure the same weight distribution between the tests. In tests without the position blocker, the assembly was adjusted to ensure the same rest starting position of the pendulum's arm. Field gap increases the influence due to the oxygen paramagnetism, yet it ensures better mechanical stability over the reconfiguration. So the tests with the field gap were more stable. So here are the drawings of the base and the whole position and stuff like that. And you have a position blocker and stuff and so on. So that's what about, and you have the dimensions of magnets and everything. Let's examine a run that didn't pass test criteria. So we have 2 runs, run 1 and run 2, and we have 3 tests per run. So if we take the average here and the average there, and we compare the difference in terms of micronewtons, we'd get these values. So for the quantum force that was detected of 100 micronewtons, we get the difference of 91 or 207. That's not very good. So this is bogus. Most of these tests are bogus except for this one. However, these values are correct, but the values for the QFN are not really trustworthy. So these values are considered garbage. So in order to get results that pass the test criteria, I had to run the tests many, many times. Roughly 15% of tests pass the test criteria. What that tells me that the qualities, the mechanical qualities of my pendulums are not that great, and I have to accept it. So in conclusion, I have to say that as much as I like the pendulum experiments and as much as I think they're extremely valuable, I have to admit that I don't have resources required to build a pendulum that would satisfy the test criteria. In that case, next, I'm going to focus on torsion balance test. And as I said at the beginning of the presentation, I'm looking for collaboration on every level. Here is my email, and I thank you for your attention.
Awesome, Mikolaj. That is wonderful. Okay, let me
Thank you.
stop sharing that for now. And then you have a PDF also. Was that the slideshow? Or?
Yes, that is, yeah.
Oh, do you want me to bring that up?
I don't know. Well, I mean, you can put it in on your website later on and stuff like that.
That was
Yeah.
what you just presented.
Exactly, yeah.
Okay, yeah. Yeah, no, that's awesome. So we've got about half an hour. Did you have more that you wanted to speak on? Or
not at the moment. That's I mean, I can answer questions here.
Yeah, that's okay. That's okay. Okay, so let me do this. Well, before anything else, then let me bring. I'll bring the usual suspects back up. Guys, put your hands together and give an enormous applause for Mikolaj. That was an amazing presentation. You have done incredibly detailed work on that. So thank you so much, sir.
I hope it wasn't too boring.
No. Yeah, you went through in massive detail. It was absolutely wonderful. Absolutely wonderful. Do you guys have any questions for Mikolaj? Yeah, Drew, go for it.
Yeah, I kind of got lost in there was so much information coming and going, but what was I mean, is there an experiment in there somewhere? I mean, did you ran the pendulum things and
yes.
you found some value? Could you just kind of give the 10,000-foot value? How do you turn that into a propeller?
Okay, so basically
I'm
you have.
Super excited
I know, but you have 2 magnets. I think, you see, my idea is very close to yours, but I'll show you how.
I'm trying to figure it out.
So you have two magnets, okay? If the field is non-symmetric, so one would be pushed this way or this way, depend, okay? So what happens is, in that case, the quantum vacuum pushes your magnets, okay? But if you push your magnets yourself, you moving energy, giving energy into the vacuum. So basically, like, you have a resistance, like a real propeller in the air or water uses resistance. Then that's basically, you created that resistance, and when you basically pushing, transferring momentum into the vacuum. You can do exactly the same thing with your experiment, because you have a difference between the plates. Okay, I have difference between the magnets in terms of force. Okay, that's all there is. But this basically that interacts with the quantum vacuum. In that case, you can, by pushing and by moving your stuff or my stuff, you can add energy to the vacuum. That's basically, you can push yourself against the vacuum. That enhances the effect so many times.
Awesome. How does adding energy to the vacuum do anything physical?
You push against it. You create a wall that you can push against. That's all there is.
Okay, so you're saying you somehow push the magnet. What does that look like to you when you push the magnet? You take your finger and push it?
Yes. You put it. You put this magnet on the propeller, and the magnet, it becomes a surface of the propeller, and you start rotating it, and you're pushing against it. You're pushing against the wall. The same thing with your stuff. You have your two plates, and you push your plates entire, and if you push against the force that is being pushed, being created, then you're pushing against the wall.
So you're saying the propeller's rotating this way.
Yeah.
And you're effectively, instead of there being water, let's say, because propellers are usually associated with water. So instead of there being water, there's the
quantum vacuum. Yeah.
Quantum vacuum, or maybe the ether or something, whatever.
Yeah, exactly.
And you're saying that you can, instead of just spinning around in a vacuum with nothing to push against, you're literally pushing against the ether, and that's going to propel you forwards.
Yeah, that will behave exactly like in the air or in water.
So you're not actually talking about spinning this thing, are you?
Yes, I am.
You're talking about physically spinning it.
Yeah.
Okay.
Positioning the magnets the way you'd position a propeller, and then you're spinning it, depend on all the force. If you have a force giving this one direction, and you start pushing in the opposite way, then you're pushing against, you're transferring momentum into the vacuum, if that's possible. Okay, put it this way. Okay, big quotes.
I don't understand how magnets work all that well. Does the field start at the surface of the magnet, or is the field inside the magnet?
Both.
Okay, well, if the field is inside the magnet, then wouldn't you just be plowing through the vacuum, whatever, inside the magnet also?
Yeah, because that's mostly vacuum anyways. Your magnet is mostly vacuum.
Magnets are mostly not there.
Yeah, I mean, all material stuff is mostly not there. There's empty space between them. It's the same thing.
So I'm just trying to figure out how you would know where the liquid is. The vacuum represents the water. And as you move the propeller forward, a real propeller runs into molecules and pushes them. And propellers operate on downwash. So your magnetic field moves forwards and slams into what?
The particles, and they have then, because your magnetic field is not uniform, the momentum is not zero, because some particles are deflected in one way and the other ones are deflected in the other way, and you see those radius are the difference. So the forces in the same. I mean, I think it's easier to.
So you're putting momentum into the vacuum, and it's throwing momentum back onto your propeller. Yeah. And that's what's driving the propeller. That's summation of that is what's moving the propeller.
It's, in your case, it's easier because you don't have magnetic field. You have simple plates, and you know which plates are being moved and stuff like that. Your forces, and that's a bit easier to explain. But again, it all depends if I'm right. Okay.
Yeah.
May I ask two questions?
Yeah, go for it, Thorsten.
Okay, one question. Did you think about, and how would it be to just move fields through so not to actually move the propeller, but to just move fields through the vacuum? That's question one. And question two, why not just build it big and see if it works instead of trying to measure small forces?
Okay, so first of all, first question, yes, the magnets of fields, it's the same as long as there's the gradient of the fields. Moving big, it's the the bigger magnets, the bigger interaction with the Earth's magnetic field, and I would have to, shelter for that. I mean, I would say if I have mu metal, I would have to have enclosure, I would say at least 12 feet in cubes, because if you take, I can shield from the Earth's magnetic field, but I have to shield from the magnets that would be attracted to the balls. So if I would have a 12 feet cube, basically with surrounded with mu metals, 2 layers, then yes, I would. That, if I'm right, it should basically just turn itself.
Why is the Earth's magnetic field a problem here?
Because it interacts with the magnets. And the stronger the magnets, the stronger the interaction. And the sort of, I call it quantum force, compared to the Earth's magnetic field is in very small compared to that interaction.
So, but that's making an experiment, and I'm more thinking of how to use it as a generator or flying with it, So.
I have no issues with how to use it, but my issues at the moment is, am I right in my experiments? That's the main point.
But when I say make it big, then it would be using it,
Yeah, but again, I would have to make sure that my experiments are right, and if I don't, I don't have that confidence yet. I think I'm onto something, but I may be wrong.
Well,
and I'm very, very skeptical.
I think it's exciting. I would say keep going, keep doing more experiments. I mean, the data that you collected was really great. I love the fact that you were really honest about your results, right? I mean, I think one of the temptations that we all have when we're doing experiments is like we're looking for things that may not always be there, and so it's easy to overinterpret. And from the way that you described your experimental results, it looked like you had a really focused, unbiased, neutral approach to it, which is amazing science right there. That's the way it's supposed to be done. So
thank you. I wish I would be right, but I wouldn't bet on it yet. Okay, I'm way. That's why I would be honored if people could try to replicate, and if they prove me wrong, fine. But if they prove me right, the better. But most of the scientific experiments are proven wrong. Anyways, that's how it is.
Awesome. Well, do you guys have any more questions, or we're a little bit ahead of time? But if you want, we can go to Bryan.
One more hint, instead of using mu metal, which is quite expensive, the Earth's magnetic field is very predictable. You can just shield it, not shield it, but just compensate it.
You mean Helmholtz coil? That's what they call it. Yeah. That's but again, that would say, okay, maybe you're interacting with the coil and stuff like that. I mean, people would always find, and I don't care I do care what people say, but I'm the biggest skeptic of all. I should be the biggest skeptic.
Just made a practical suggestion, that's all.
No, I know. I'm thinking
from that point of view.
I agree with you on that. Yeah, but that's one of the things that when I do the torsion beam experiments, I'm thinking of having a Helmholtz coil, just one direction, not 3D, but just 1D. That would help. Yeah, thank you.
Awesome. Well, guys, if it's okay, we could go to Bryan early,
So maybe I have one more talking point to this.
Yeah.
So first of all, thank you for the presentation. It was very interesting, and I agree with certain points. I think that the points I really agree with is like field geometry matters. Vacuum is not just trivial emptiness, and local structure may matter more than total field strength. I think this is also a very interesting point. Non-uniform fields may induce non-trivial state organizations. This is something I've heard out of your presentation. I think I totally agree with that statement. There's also some stuff I don't know if I do not agree or do not fully understand yet, but I really like your presentation, and I also like that you view your experimental setup as something that people should test and falsify, right? This is the exactly right approach. And I want, have you considered maybe reformulating your theoretical view, like to view the effect not as a direct momentum transfer from semi-classical virtual particles, but as a geometry-induced vacuum state asymmetry? So there could be different observable scaling laws which could be distinguishable from ordinary dip angle torque and release condition bias and stuff like that.
That could help,
So-
but you see, look, I design chips for a living. Okay, so that's where I used to design radio towers like 30 years ago. So when the cell phones were, walkie-talkies, no digital, but I don't have enough background. Okay, and then you see, my work is very demanding. So this is my hobby and stuff like that. I mean, I may agree with you. I would consider these things, but I don't have enough background to basically even go into these details, and not enough background, not enough time. Okay, so if I retire, then I'll start studying and I consider it. But I mean, I agree with you. It may be something else. If the results are correct, that it's not necessarily based on what I think it is. Okay, based maybe on other things.
Thank you.
Awesome. Okay, well, guys, let's put our hands together then. One more time for Mikolaj. Mikolaj, thank you so much. Thank you so much. Keep doing experiments on this. I would love to have you come back and give us updates on it. And,
I will do that. Yeah.
Yeah, absolutely. Okay, so let me do this. We're a little bit ahead of time, but that's okay because it's going to take me a moment to get. Oh, in fact, there it is, Bryan. So I have your presentation up. So guys, for anyone who doesn't know, Mr. Bryan St. Clair has been a long time regular participant and attendee at the APEC conference. You have done incredible work with heavy duty industrial scale inertial propulsion devices. And so I actually asked you, I think 2 months ago, if you'd be open to doing a past, present, and future, because you have done so much in this area and it's such incredible quality work. So thank you, sir. Thank you very much.
Well, thank you for inviting me. Can you hear me okay, number one?
I can. So let me do this. Why don't I take myself out and if it's okay, launch right into it, and I'll be here in the background.
All right, perfect. I appreciate it. All right, well, as Tim said, he asked me to do a presentation on the Pi system, what I've been building now for the last, 5 or 10 years, experimenting with and upgrading and changing, and until finally I think we've got something that is pretty good. It's not quite finished, but it's pretty good. So covering the past and the present and hopefully on into the future. So from the beginning, I started St. Clair Tech R&D as a very casual entity back in the 1980s and 90s. We've evolved from carburetors and fuel systems, fuel savers, energy generators, emission controls, and then now finally onto propulsion systems. Inertial propulsion, I have personally started the Inertial Propulsion Workshop. I refer to it many times as just the workshop. It's the latest chapter in the St. Clair Tech R&D story at this point. This was created to help promote the technology and hopefully to teach it to other people who maybe can improve it, do better, and spread it. I don't want to be the only one looking at this saying, hey, I can make this work. I think other people need to replicate it and do some of this on their own. In that, I do have a builder's manual, which comes with some one-on-one consultation. And I want to see people be able to succeed with this stuff. So our focus, my focus particular, is hardware first demonstrations. It's not theoretical speculations, and I'm definitely never hung up on the math. Some of that math to me just doesn't math. Theories that don't come to fruition, and I'm just simply building real machines that hopefully the math will catch up with and be able to say, oh, that's why you're doing what you're doing. I have an extensive background in mechanical systems, and I've done a lot of repair work. I've been building and testing machinery since the late 1970s. Made a career out of motor vehicle repairs. This has given me a pretty strong background in making things work. Sometimes the engineered devices just don't work the way that they're supposed to. And so that's been pretty much my career for the last 40 some years. Primarily building with an experimentalist approach is where I go. Just like we did with farm machinery, muscle cars. I remember going out on the strip at 3 o'clock in the morning and, you know, winning a few beers here and there. A lot of that comes from trial and error, from experience, and what you just feel is going to work, kind of from the gut. So now with over 10 different generations of propulsion hardware behind me, yes, 10 generations of propulsion hardware. We're up to the Pi 7.1. This is the most ambitious build so far. And I do want to say that everything so far has been privately funded. We've not asked for any money for any of this stuff. So therefore, we are literally beholden to no one having to do with it. So first, I want to talk about what it's not. This is not anti-gravity. It's not a warp drive. It's not magic. It is not disagreeing with science. It is not disagreeing with math. And it is not putting anyone on the spot saying anyone is particularly right or wrong. What this is doing is simply saying there's a different way to go about it. We have a mechanically timed epicyclic, I keep trying to mispronounce that, epicyclic drive system. It's thoroughly respectful of all the laws of physics, and it only questions the status quo of the application of those laws, not the laws themselves. This is an observable, measurable mechanical energy. It's an exchange system that creates movement without expelling mass. And it generates linear impulses. These linear impulses create thrust. They're created through a controlled timing and directed system, which uses a lot of impulse redirection. When we make impulses, many times they're going in the wrong direction as well as in the right direction, and that's exactly what the redirection has to do. It has to eliminate what's going backwards, or at least minimalize it to where something is now going in one direction with more force than it's trying to go in the other direction. Leading up to the Pi, I started out back years ago with Roy Thornson's system. It was called the Ezekiel. He called it that because he wanted to equate it with Ezekiel's wheel in biblical studies. And then he also coined it as an energy zone kinetic lifter, Ezekiel. His system used magnetic traps, mechanical traps, different things that would stop the motion internally and hold on to it. They were a huge energy drain on the system, and it was not efficient. And even though it wasn't efficient, it still worked, which is really, really awesome. So from those energy traps, we now have moved to directional energy release. So instead of trapping and stopping and using up energy, we redirect it we might have a stopping impulse, but we're not wasting that energy. We're putting it back into a forward motion. We've tried to eliminate those inefficient braking mechanisms that I feel was really part of what was holding Roy Thorsten back on some of that. At this point in time, basically, we have a very crude version. Think Model T versus Ferrari. Right now, we're still in the Model T phase. This thing is banging along. It's making some thrust. It's able to push. We've tested it out in the real world. We've created some serious proof of concept devices. Our short-term goal with this is supplemental thrust for both all ground, water, and aerospace systems. And by supplemental thrust, think hybrid vehicles. They may use their own energy-producing systems. This is an addition to it to make them more efficient. Eventually, I think that they're going to be a primary motive system. I think that we'll be able to use them as a primary thrust source to move around virtually anywhere. The pi mechanics. The mechanics of it is the pulse. It makes pulses. And a lot of people don't like the fact that I'm making pulses, and they feel that the pulses are just a vibration that's making this move. Well, that's possible. I'm not going to discount that possibility. But pulses have been part of every single mechanical thrust system that we've had since virtually day one. If you go all the way back to oxen or horses, every single step they took was a pulse. When we moved on to internal combustion engines, every time a piston fires, it's a pulse. Those pulses get smooth because they're overlapped and they use flywheels, and there are a lot of different mechanisms in there to eliminate the harshness that those pulses cause. But the pulses are still a huge part of it. The unique epicyclic geometry we use creates a nonlinear velocity profile. By nonlinear velocity profile, I mean that it does not remain the same through the entire cycle. It's directed. Momentum energy harvesting. That we talk a lot here about energy movement and energy harvesting, and that's exactly what we're doing. We're building some mechanical energy. Call it inertia, call it ZPE, call it Aether, call it anything you want to. I really don't care what we call it. The point is that we're building energy and we're redirecting that energy without expelling mass. We're only moving energy. So the momentum energy harvesting is done through rigidly controlled velocity changes and a smooth flowing redirection. And that's really everything that it comes down to. When I started building these, I was following everything that Roy Thorsten had done, because I said, hey, here's a system that works. I wanna replicate it. I want to see what we can do with it. Let's see where his system didn't go any further and why he stopped where he did. Well, back to the whole braking problem. The braking systems that were in it, what he called energy traps, they were literally were brakes. And he would put the brakes on internally, wasting valuable input energy and not translating that back into thrust. When he would release the brakes, suddenly now he had thrust all over again, and that's how he was able to get it to work. With the way that we're doing this, the masses that we've got moving around, the weights, rather than putting a brake on them, we do have an arresting system. The system is arrested. the weight moves, an arrestor catches it, but when it does, that catching, that is changed into forward thrust. Then it releases it, where it builds energy again and catches, and that is translated into forward thrust. We're not wasting anything more than we can help. Over time, we have improved those stop systems, and we've created some repeatable and measurable thrust. It's definitely correlated to timing adjustments, and timing has become very, very critical in the system. We can still get thrust even when the timing is grossly out of adjustment, but now we are truly going for an efficient system that will move forward without wasting energy because it was out of time or because it had something in the system that was just blocking the flow. Basically, we find a sweet spot. The sweet spot alignment is assumed by mass flow calculations, and they are confirmed with empirical measurements. Yes, we still do the math, but we use the math in accordance with what we're doing on the workbench. We're not building what we have on the workbench to match the math. We're using them hand in hand together. Our current in-house focus is on improving efficiency and refining the platform entirely. So one of the first things that we have really done that was a huge game changer was the integration of an experimental dead blow weight system. In the shops, I've done so much mechanical repair for so many years that hammers, of course, are always something that are used and hopefully used efficiently, but the most efficient hammers are a dead blow hammer. Now, that doesn't make them hit any harder, but it does eliminate waste in that system. Instead of having a hard impact that's translated into sound and translated into heat, we have an internal weight system that follows the original portion of the impact and lengthens that impact duration. And by lengthening the impact duration, we make that impact more efficient. I was having a discussion with a colleague about how to lengthen the impact, and he kind of offhandedly made the statement of, boy, it would sure be nice to have an inertial capacitor, something we could charge up and then release slowly. And it hit me at that point, well, there's our dead blow. Dead blow hammers, that's exactly what they do. From there, we moved on to the speed differential control. We didn't move on to it. These things were all developed pretty much at the same time, just on different workbenches through the lab, through the shop, and pretty much assembled one at a time to make sure that we're not going to miss something, because you can't make too many changes at once. Otherwise, you just don't know which one caused a better motion, a worse motion, or something counteracts something else. The speed differential control was actually built because we found a slipping belt. I had a belt that would slip every once in a while, and I didn't realize it was slipping. But when that belt slipped, I would lose 90% of my thrust. And so once I realized that that's what was happening, I decided to try just the exact opposite. Instead of having it slow down because the belt was slipping at that exact moment, I marked out that moment on the machine and was able to physically speed it up at the point when it was normally trying to slow down. And that actually had a huge improvement on how it was functioning. And now, after the Pi 6, the 6 was built for one purpose only, and that was to introduce the world to the quantified backlash drive coupler. The QBD coupler is basically something that couples two halves together with an allowable amount of backlash between those two pieces. And that allows those two pieces to stay within a certain amount of synchronization and still be able to operate somewhat independently. And by being able to operate independently, one doesn't affect the other one. And we were able to get virtually two different pi systems working in sync and yet not affecting the other one. And that overlap was a huge game changer. That is now something we're building into the overall design of the Pi 7, which is now becoming a Pi 7.1. That's kind of bringing us from the Model T stage closer to that muscle car stage, but we're still throwing a supercharger on a Briggs & Stratton engine. It just doesn't have the power yet that we really need. So let's get right down into the nuts and bolts of this thing. First, the architecture overview. We can use either a single or a dual planet gear. They orbit a fixed sun gear with the mass attachment points cycling in the radii, and that creates a velocity change. And that's the momentum to energy movement that we generate. Pivoting masses contact those internal stops. When they contact those stops, they have an instant velocity change. Energy exchange through momentum exchange is really where we're going with that. And then we also use the modified cardioid geometry, and I know I mispronounce cardioid constantly. My wife reminds me of that. We use that modified cardioid geometry, which defines that impulse cycle. That it's really and truly the same geometry that Roy Thornton was using. That I want to give him 100% full credit for. He did a lot of very groundbreaking work on this to bring it to where it is today. Having to do with that, when the mass comes around to the center of the unit, we cannot, one of the rules with this is we cannot allow the mass to cross center. By not allowing it to cross center, number one, we make it more asymmetrical, but we also create a small forward pulse. Now, in Roy's devices, that small forward pulse when the mass would hit center was literally the majority of his forward impulse. And that's where he was getting a tremendous amount of his power out of that system. We are still using that, but at this point in time, that is literally about 20 to 30% of our forward thrust. The rest of it is generated later on in the cycle. We translate that forward thrust, that momentum, into the center pin, the center axle, whatever you'd like to call it, to push the system forward. Pardon me. This is a lesser, but it's still a critical moment for the preferred direction impulse transfer. It's one of two sharply defined and timed pulse events that each mass produces in any one single orbit around the sun gear. Every time they make an orbit, each one of the masses has two impulses to move forward. So we're generating just as much efficiency as we possibly can by doing that. The more prominent pulse comes from the outer stop. It's an impact position that is constantly moving with the machine. That impact, that stop, is actually on one of the planet gears, either one of the planet gears rotating around the sun gear. And that stop is only there to stop the mass from swinging any further than a forward position. Once it's virtually in line with the center axle of the pi and the center axle of the sun gear and the planet gear, that at that point, that's where the stop needs to effectively limit its motion, and that translates that force back into the planet gear, back into the sun gear, into the center point, and into the chassis of the system. And that is where we're getting the majority of our pulse. That is also where the dead blow was most effective. It stopped some bounce on the center point, but this is where it was most effective in creating forward thrust. The proper mechanical alignment obviously is a really big deal, and contact timing determines the performance output. There's just no two ways around that. That's where it comes down to critical timing. Sometimes we have to actually add pieces and parts to hold something in place a little longer, or grind something out of the way so that it moves a little faster, a little cleaner, a little better. Correct precision tuning of this stop's position is truly required for maintaining directional movement. And if you look at the picture on the screen, the stop that you see contacting that mass is a threaded bolt, so we can actually do fine-tuning adjustments on that to wherever it needs to be to make the most effective and efficient forward impulse. Back to that dead blow weight, that was a huge innovation. And what we did is we created the original masses. I've got a couple of them here. The original masses were just these solid metal pieces. They were a lot of small pieces that were welded together until we got the right mass, the right weight, what we needed for it. But what we did is, this is literally one of the ones that you're seeing in the pictures. And it's hollow. The inside of it is hollow. It's made into a box, and then it's filled with shot. Sometimes you can hear it rattle, sometimes you can't. That shot acts as a dead blow system. That's our inertial capacitor that extends the impact time to increase the measurable thrust. It also, of course, minimizes that elastic rebound, what we talked about, it bouncing when it hit the center pin. And that was a big deal. To stop that bouncing just made it that much more efficient. We're not wasting energy. Now the sun gear, the center gear, the one that those planets rotate around, this is one of the early planet gears. Obviously, it's something that we made in-house. It was very coarse, it was noisy, it was messy, but it worked. And because it was inexpensive and simple to reproduce, we didn't really care as much. Well, we cared, but not as much when we would damage one, as if we were spending about $300 a piece on those gears, which is what I was quoted from a machine shop at the time. And honestly, I didn't want to destroy $300 gears by playing, guessing games with timing and with different pieces. That sun gear has to be adjustable. And the reason for that is where the timing comes from for the mass to hit the center pin. It really kind of changes it from, with all these adjustments and the tuning, it almost changes it from just a somebody beating on a pan with a spoon into a more tuned musical device. Its music is thrust. It's not musical to listen to. They're noisy, they're loud, and they're messy, and that's just the way it is. It's been found that very small timing adjustments can sometimes equal very large output variances. The speed differential controller, which I talked about having come from the point where it was slipping on a belt, and this counters that whole effect. And literally, it's like putting a turbocharger on an engine. It's forcing more momentum into the system at the point where the momentum needs to build. It's just before the point of that forward impact. Now, when it's running two masses and two planet gears, it's also working on the backside. So it's also increasing the force when it hits the pin in the center. That helps, it does, but that's, again, just not where the big deal is. That alone doesn't create anywhere near the thrust that I need to make this a viable machine for propulsion. That speed control differential, it eliminates the motor lag that we get under load, so that we maintain propulsion, and when we boost it up just a little extra, that's where we get our boost in power. And it's literally the fusion of the electronic timing and the mechanical momentum coming together to make a synchronous machine, which is an oxymoron when it's a synchronous machine that causes an asynchronous pulse. The heartbeat of this, the cycle of it, I've talked about that, and many of you have seen the videos on YouTube that I've got that show the cycle. But literally, the cycle is very, very simple. It's almost a four-stroke, like a four-stroke engine would be, where we have the mass come around and it hits the center pin. It stays on that center pin for a duration, and then it's released from the center pin where it comes around and hits the outer stop, where it stays for a short duration, and then it comes back around and it cycles back in to where it hits that center pin. So our center impact and speed increase and mass acceleration all work together. The outer impact is a momentum harvest, and it moves to speed normalization. And then the time speed increase obviously positively affects the center pin impulse along with the outer stop impulse. So where do we go to advance this technology? Mechanical vector biasing. I don't like using big words. I don't like throwing around buzzwords. They're inefficient and ineffective in my shop. Basically, we shunt some parasitic forces, and breaking the symmetry via the high velocity power arcs within the system. It's all accurate. It's all true. It's all real. Just like impedance matching in an antenna system or in an audio system is very important so that we don't get feedback. Impedance matching in our pi system is important for generating forward momentum. It can be viewed, if you're a scope person, it would be viewed more of a modified sawtooth waveform. A standard sine wave is smooth, it's clean, it's dynamic, everything flows very, very well. It's an efficient way to transmit electricity. It is not an efficient way to generate forward momentum. And then the last thing that we use, and it's something that's very seldom talked about, is an inertial force time lag. There is a time lag that's measurable when something impacts, between the time of the impact and the time that whatever it impacts moves, there is a time lag. That time lag can be used, and by using the dead blow masses, the dead blow weights, we increase the amount of time that it stays pushing all the way through the time lag, and now it's still pushing once the time lag is actually done and over with. It's kind of an oversimplification, but it kind of allows the force to outrun the time lag. It's not cheating the system, but it's working with the system, and it's overcoming a shortcoming within it. Our newest item, as I talked about before, is the quantified backlash drive coupler. The QBD coupler is, I've got one back here on the bench that we can take a look at in a couple of minutes. It's the same one that's in the photograph that's on the screen right now. And it could be kind of seen as a half-wave rectifier. If we're still thinking about waveforms and lab scopes, instead of having a non-rectified sine wave that doesn't do us any good, and instead of having a quarter wave rectification, we have a half-wave rectifier. So we're rectifying on two sides of that. And every time it's rectified, instead of losing power, we're changing that from what would have been the bottom side of the sine wave into a forward thrust impulse. This also, it can be called a timing gate because it is a gate system between two rotating assemblies. And what's really nice about it is it allows two motored systems, two separately powered systems, independently to be able to accelerate during their power arcs and not affect the other one. If we have the acceleration at the wrong time, it's actually a detrimental effect. So if we're locked together, we can't have them overlap at a 90 degrees situation and still be able to use that speed control differential to boost the pulse system. What was really the nicest thing about that is that not only did it make it stronger, it made it so smooth when I was driving down the road testing this, that other than the noise that I could hear coming from the back end of the vehicle, you wouldn't have known that it was back there pushing the vehicle along at all. It was very efficient, and it was very smooth and very clean. So to bring it down to, a bunch of this stuff, into a overlap synchronization system, we use the swing arrestor, the QBD coupler, the primary energy overlap synchronization point, so that the two can make energy and then direct it properly without affecting one another. The dead blows in our center picture there, you see the weights, these weights without any dead blow capability, they bounced, and that's all there was to it. They bounced, and they were not as efficient because they would bounce back. So in the photograph you see on the right, we have the refined impact stop. That enhanced the performance dramatically, plus it was very, very easily adjustable. That, combined with the fact that that is a picture of one of our dead blow weights being used, made that a very efficient way to generate thrust. Practical scaling of it, well, that's the future, really. Depending on an application, this would consist of either pairing symmetrical counter-rotating units so that the pulses would overlap without negatively affecting the paired assembly. But in counter-rotation, we wouldn't have the torque being put on a craft, let's say, that was in the air or it was in space, in orbit. It didn't have a mechanical grounding to keep it moving in one direction. And of course, the QBD cancels the objectional pulsing while increasing the forward impulse. And now, through the Inertial Propulsion Workshop, it's a school group that I put together, School SKOOL. It's a group that I put together where we could get together as a small community, a small group of people, and exchange ideas without having undue influence from, let's say, some bad actors that would sometimes get into certain forums. We don't have that problem. It's a good, safe, solid place where we can get together and share ideas and information. Moving on from that, this was really kind of pretty close to where my presentation was going to end, but that's when I heard about SATCOM Week. I'd never heard of it before. So I decided that that's not where this presentation should start coming to an end. That's where we should talk about something slightly different. And that is the fact that Genergo actually is putting some inertial propulsion systems in space and promoting it publicly. I didn't have the opportunity to go to SATCOM Week myself, but Ross Small, who works with me from time to time on different things, was able to go down. He got me some really cool memorabilia. That's a shoulder patch or an emblem. Genergo is one of the very first that we've seen in many, many, many years that has openly stated that they are building a propulsion system that does not expel mass and yet works in zero gravity, microgravity, orbit, whatever you would like to call it. Some real excitement is coming from that announcement and from what they're doing. The best that we can see at this point comes from the patents that they've filed. Ross tried to talk to the engineers. The engineers were more than happy to talk to them, but they were not willing to talk about the nuts and bolts of how the system worked. I don't blame them. I don't blame them at all. It's a really big deal, especially for them. But looking at the patents, we're kind of somewhere around the Henry Bull type work. They're moving magnets, and that's why I was so interested in hearing the last presentations about moving magnets in space to create thrust. Genergo is moving magnets, but they're not moving them in a rotation. They're oscillating those magnets back and forth. They're using electromagnets to cause the motion, and then using the effects of the magnets instead of mechanical springs to keep impacts to a minimum and yet generate thrust. Now, that's a super oversimplification, but quite honestly, that's about all we've got at this point, because they're not letting anything out. It's a new technology for them. What's absolutely amazing to me is that they are actually promoting it. They're in space, they're using it, they're public. They've come to the United States. Genergo is an Italian company, but they've come to the States. They've launched from Kennedy Space Center here in the United States, and now they're talking about it. They're putting it out there for people to see, and I don't know why we're not grabbing the attention that we should from it. This kind of leads me to talk about something, that we really don't talk about much. The fact that in conventional propulsion systems, there are many offshoots. If you simply take aerospace, it's such a huge umbrella that covers jet engines, rocket engines, propeller engines. It covers hot air balloons. It covers weather balloons, lighter than air, dirigibles. It covers so many different things that each one of those has a dozen different sciences that go with them. But with inertial propulsion or alternate propulsion systems, we haven't been afforded that luxury because the mainstream didn't agree that we were able to do any of this stuff. Now that we're starting to gain some notice amongst the general populace, I think we can actually start to call it a more of an umbrella of a universal propulsion system. And so if we have universal propulsion, that's like aerospace propulsion. A universal propulsion, however, is not just limited to aerospace. Universal propulsion would also be able to be used on the ground, in the water, under the water. It can be used anywhere, anytime that an extra pulse of propulsion is needed. And that would kind of cover a huge number of different sciences that would actually go along with it. I made a list at one point of all the different variations that there are, the major points of variation for conventional versus alternate or universal propulsion. And there are actually more separate, smaller sciences in what we are doing here at APEC than there are at what they're doing in the generic aerospace industry. That's not to say that they're not doing tremendous work, because they are. But we have a huge number of things that we're doing, and I think it's time that we start getting recognized for that. Not myself personally, but all of us as a community. So that does bring me to a real and true closing. I'm going to wrap up. Theory is the map. Hardware is the territory. And now that we're transitioning towards a genuine universal propulsion system, it's time for people to start coming together, working together. That's what APEC has been about since day one, and that's why I love being here. And that's also why I started the Inertial Propulsion Workshop. I refer to it just as the workshop. And it is a small community of us builders that get together and are able to share ideas and work together for some of this stuff. And right now we're literally working as a community on the Pi 7 and the 7.1 to bring that into where it needs to be. On the workbench, just over my shoulder, we do have the Pi 6. And I don't think that the camera is going to really catch this as well as I would like it to. But this is the Pi 6. And this is that QBD drive. So the top can move this far without the bottom, or the bottom can move that far without the top. And it allows each one of them to overlap without affecting the other one. And that will also bring us to the Pi 7, 7.1. I've still got it on wheels, so I can move it around here. And right now I've got the coupler taken apart. This one actually has a coupler that I can couple and uncouple as needed. So right now that you would see them lined up, but they can also be at a 90-degree offset from one another. So one can move and the other one not. And this is actually part of that coupler system right here. It's taken apart and for the main purpose of we're rebuilding these masses. The weights were built I feel incorrectly to begin with. This is the last one that has the original build. We've still got the ramp on it to keep it held in for a longer duration. But because of the way that it's designed, it's not getting maximum impact. Rebuilding them so that they're reoriented, that's causing a much more efficient impact. I can run just the top one right now. I've got the bottom one unhooked. But you can see that it rotates smoothly, it rotates cleanly, and it's really not very noisy either. The wheels that are on this cart, I didn't like them for the longest time because it takes over 10 pounds of force just to make the cart move a little bit. But now I'm kind of glad that it doesn't move quite so easily because I can run this and it doesn't scoot across the shop on me. I put it on wheels, on smooth running wheels on the concrete floor, and it really does. It runs across the floor. It works very, very well. So I don't know what else anybody would like to hear about. That pretty much brings me to the end of my demonstration. I'm open to all kinds of any questions anybody has. So Tim, that's it for now.
Bryan, thank you. That is amazing. Your work is truly inspiring. Truly inspiring. I'm going to bring let me see. I think I've got, oops, no, that's not. I'll bring Drew's alien in too. Guys, let's put our hands together for Mr. Bryan St. Clair. Bryan, I love your work. I cannot say that enough. Like, this is with inertial propulsion stuff, I've seen like scale model prototypes, right? And like a lot of folks, when they try and build that, it's flimsy and it flies apart and breaks. And the work that you're doing, like the craftsmanship and the scale and the quality you put into it is absolutely remarkable. So, yeah.
Well, a lot of the work that I put together, you talk about craftsmanship. Well, there is some craftsmanship that goes into it, but it's also a price point because I've destroyed hundreds of pounds of components over the last 5 or 10 years, and it would have broke me. I wouldn't have been able to continue if I wasn't building some of this stuff myself.
Yeah. Well, and probably being able to build it heavier duty helps with that, right?
Oh, absolutely.
Yeah. Again, absolutely remarkable. Yeah, and you have come on many times before, and every time, I mean, it's more like better quality, larger. I mean, I love your work. So people should definitely check that out. They definitely need to. And so that's in there for the replay, the St. Clair Tech R&D website. So I've got that. And then I should ask, guys, do you have any questions for Bryan? Mark?
Yeah, I got a question.
Sure.
So with all the research that you've been doing and getting up on to Pi 7.1, do you see any path forward to a solid state system using, say, like liquid mercury?
Yes. Short answer, yes, I do. There have been some systems that I've been involved with that there are some NDAs involved, so I can't get into details. There have been some systems that I've been involved with that used a liquid format. They do work, but they have never worked to the way that they were intended to. Quite honestly, because they were following the math instead of building it and letting the math follow them. I mean, it's a lousy way to have to look at it, but we've been taught all this math for so many years that we'll build something that doesn't work. And then when you build something that does work, the ones that have taught the math say it can't work, and they just dismiss it because it doesn't agree. So you know, we're building, and let the mathematicians figure it out from there. Let them see why it works, and then they can actually design better systems. And I think that's exactly where we're going to start seeing liquid systems, mercury or some other heavy liquid. Mercury is ideal, obviously, because it is such a heavy liquid, and it's conductive, and it's got some other really cool, unique properties that we can utilize. But quite honestly, any heavy liquid system, I think we could probably build something eventually. We're just not there yet.
I've built some systems using heavy liquids, and I've seen some results as well. But
Yes.
kind of got to a standstill. I'm not really sure what to try next. It is pretty daunting to build something, you know, with a liquid system is a lot harder than just gears and weights. So you put a lot of effort in the upfront before the experiment is even ran.
Oh yeah, absolutely. And I've run a lot of those experiments here, and you're right. There's a lot of building to find out that you were absolutely wrong, or a lot of building to say, well, that works, but it needs to be completely redesigned. It's a lot of work, and unfortunately, the math doesn't lead us there. The math has to follow it. And it gets timely. It gets expensive. It's a pain in the butt.
One thing that strikes me is you know, I'm always looking at this, like I always try and look at like levels of applications for it. And one of the common criticisms of this technology is people say, well, it's a slip stick reaction. And then another criticism is it's partially constrained motion, right? Like for instance, if it's pushing up or down or sideways, and the wheels can't roll sideways or it can't move up or down, and then it creates this forward thrust. But one of the things that I've always viewed that as is like going back even to the 1970s to Roy Thornson's canoe. These technologies are absolutely proven to work. Like
yes.
On a surface or in liquid or in the air, right? So if it is constrained motion, the only thing that critics would win is not working in space. It still works everywhere else. And I think that opens up a world of applications.
And quite honestly, we've put these on balls, you know, so that they'll move in any direction on a plane, obviously, but they'll move in any direction on that plane, and we get a unidirectional force. We're not just scattered all over the place. Part of the problem when engineering this is the force is wide, and bringing it narrow enough to be a true directional
Vector.
force, the vector control, correct. And that's where putting them on the ping pong balls and the ball bearings on the steel workbench came in. Okay, let's find out where we're losing it, you know. And it turned out that we were simply losing it by sidewards directions. And once everything is aligned and proper, we get a lot of directional force. As far as the stick slip, that's great. That's a great idea. It could be. I'm not going to dispute that. But I will say that if it was truly a stick slip design, we wouldn't be able to put it in a moving motor vehicle and see it get more powerful the faster we drive.
Yeah. Yeah.
I don't see that as a possibility at that point in time. I'm not going to say it's not a possibility, because I could be wrong, just like anybody else.
Well, and you know, in terms of the physics backing for this, I read an elaborate proof by Dr. Gennady Shipov, and he was talking about what he called, I believe it was Einstein-Cartan. It was derivation of Einstein-Cartan theory. His approach to torsion basically translated into exactly what you're building. And he had a device on a table. You may have seen videos of that, but he had a device on a table doing very similar things to what you're doing, except of course yours is much larger in scale. So
right, and I did actually build a test rig similar to his, and it would work. There's no question that he was definitely not faking any part of that. It was entirely real and true and possible. It wasn't what I wanted to do, and it wouldn't, even at the lower scale that I built a model, I couldn't get it to produce the same amount of power that I was getting already with a system that didn't work right. So I said, you know, we're going to put that on a shelf someplace, and we'll keep it in the back of our mind, and we'll keep doing what we're doing until we decide to do something different.
Do you ever try gyroscopes?
Yes, I have. In fact, in the workshop, one of the guys in the workshop asked if we could talk more about gyroscopes, and I said, absolutely, let's talk about gyroscopes. And in the workshop, I in particular, but with others' input, we put together a test rig completely from scratch using a tiny little electric motor spinning a very small gyroscope that would cause a forward thrust within the machine without reversion that would cause another, and it was cause and effect, cause and effect, cause and effect. It would cause that motion without reversion so that that motion could cause a forward impulse. And then it would return without having any of those reverse effects. So absolutely, I don't see any reason why gyroscopes couldn't be put to use in all kinds of ways, just like Mike Gamble is doing.
I built a device like Mike Gamble's. When you just have two arms and you put it on a pendulum, it would swing up and down. But when we had 4 of them, I was actually able to get it. And this is on a pendulum, so it's swinging around like that. And it can also move up and down. So you can see if there's any translated force in the vertical.
Yep. That's a perfect way to do it. Just putting them on a swinging pendulum, I don't think that that's a proper way to do it. But to put them on a balanced beam that is also able to turn, so you've basically got a low friction gimbal system.
Yeah,
that's an ideal way to find out which way you've got motion.
Yeah, and it's kind of difficult to do with something that weighs as much as yours, because you would need a forklift and you would need like a serious I-beam to do it, but it is possible.
I've actually got an I-beam standing over in the corner of the shop that was earmarked for some of that work.
Do you have a forklift?
I don't have a forklift, but I do have an engine crane.
An engine crane might do the trick, yeah. And then you need some heavy lead weights for the other side.
That's
or you
it.
could put the Pi 6 and the Pi 7 and just like have them fight it out.
There you go. Yeah, I mean, you're right though. That is a great way to do it.
And you could, in theory, you could run these in, I'm not going to use the right word, you could run these in parallel, right? I'm almost thinking of like pistons in a V8 engine, right? Where like, so in a multi-cylinder engine, each piston fires and you get a pulse. With yours, you could have several of these like next to each other and they all strike at a different interval, right?
Yes, and that's where the QBD coupler came in, is so that they can strike at different intervals without affecting one another.
Okay.
At first, I didn't know because I had tried previously. I mean, this was several years ago. I had tried running 2 of them together on the same platform with 2 separate motors, and sometimes they would work together and sometimes they would fight one another, and I couldn't keep the synchronization correct to keep anything working properly. And that's where it came back to this. It's like, I need a way to have them synchronized without effect, you know? And you're absolutely right. I mean, you could put 20 of these together and holy cow.
Yeah. And
what would it take to get you into outer space, or to build something that's worthy of going to outer space?
We're getting there. We're getting really, really close. Once the 7 is 7.1, it's liable to be a 7.2 or a 7.3 by the time I get there. But once that's really working properly, that would be the platform to build a little bit smaller so that it would run cleaner and be more transportable. I've already upscaled and downscaled, so I know that scaling is not an issue. We had the little Pi Mini that has one ounce weight, and it'll still pull a 2-pound unit across the workbench. It runs on a $10 Harbor Freight electric screwdriver. You know, I mean, you can really get inventive with some of this stuff if you really try. But it's scalable, which is great because that proves that it'll run it small, and this proves that it'll run it large, and everything in between has just proven itself out.
How big are the weights on this one?
These weights are about 6 pounds.
Oh, wow. Yeah.
They're hollow. They have 1 pound of steel shot inside of them.
Now, we have like 4 pound or like 3 pound gyroscopes over here.
Mm-hmm. I mean, you can do a lot of work with 2 or 3 pounds. You really can.
Oh, yeah. Oh, yeah. And when it's rotating at 10,000 RPM, it can move mountains.
Oh, yes. I've had a good number of gyroscopes come apart on me, and they'll dance across the shop floor for a good long time.
Have you optimized the thrust to weight at all enough to have like a nice number handy for best thrust to weight you've gotten?
I don't, mostly because there's so much waste in the system still. This is the most efficient one that I've built. Everything in there has got ball bearings. There's nothing in there that's a bushing or a mechanical slide or anything of the sort. The only things that are not optimized will be the impact points, and that will be the next generation along the way. But honestly, that's the least of its worries. That once we have this one up and running, we should be able to measure what it takes to make it run out of time so that it doesn't actually produce any power, and then see it run in time, measure the power output, and we should get a more accurate measurement at that point.
So very interesting, a very, very cool presentation. And I totally agree with you that physics should actually model what experiments show, and physics should actually model what all experiments show, and not just experiments that conform the standard model or the current doctrine of physics.
Absolutely. And there's a lot of experiments. There's a lot of experiments
on the theoretical side as in the. Yeah, I agree. There are a lot of experiments that already go outside, and the book of Kuhn about the structural of shifting paradigms in science, right? You need a certain amount of experiments going beyond to actually force a breaking point, and I hope we're getting close. And it's very important that we have as many experiments that push towards this breaking point, and at some point. You will get physicists who try to model this kind of experiments. And I think we do have some physicists also around the APEC community who are actively trying to model the experiments. But the same as with the experiments, the theoretical work is very difficult, and it costs also money, and it costs time, and it would be much better if you would have centralized institutions with whole teams working on it. But the reality is we are sitting in our garage building it ourselves, right? But we're actually doing it. A lot of people in the APEC crowd are actually doing it. And so I'm personally working more on the theoretical side. And I find your setup very, very interesting. And I have a question. So you described the system as a tuned instrument with narrow timing windows, right?
Yes.
Have you mapped the full parameter space for to see whether output appears only in very thin islands, or like that would be expected of a threshold governed dynamics model, or are those like larger time islands? How precise does it have to be? Do we have mapped it out?
How precise does it have to be? It doesn't. It doesn't have to be precise at all, and it'll still work. It's how efficient do you want it to be? Mm-hmm. And the tighter that you get into the correct timing and the correct adjustments, the more efficient it becomes. And I can have this thing, 20 degrees out of time, and I can still make power. It'll still move, but it doesn't move well. And, the closer you get to the correct parameters, the better it works. I fixed automobiles for so many years. I bring it back to ignition timing. I can make your car run at 30 degrees off, but it isn't going to like it, and you're not going to like driving it. But you bring it down to where it belongs, and within 3 to 5 degrees, you're probably not going to notice the difference in how it runs. That's within that optimal range. After that, it's just bringing it down even closer for emission controls and thermodynamics.
Mm-hmm.
Hey, I've got just a basic physics question. You're putting energy basically into rotation, and then you're extracting it back out in linear.
Yes.
So you're basically converting rotational energy into linear energy. Wouldn't you just be better off putting that energy into the engine, or putting it into the wheels? Just put
that'd be great if that'd be great if the wheels would contact the ground in an airplane or a spaceship. I mean, this will literally push anything. It doesn't matter what it is. It could push a boat. It could push a car. It could push an airplane, a drone. Think drones with that are fully electric with no thermal output in any way. You think of a small
every day.
Think of a small spaceship that only requires a small amount of power, just like what you're building yourself. It only requires a small amount of electricity, and it can move. This thing is running 2 electric motors and still not drawing more than about 10 amps. That's pretty incredible.
A lot of power.
That's a lot of power for that little bit of input.
Well, but what do you get for those 10 amps? Amps times volts is power. So
right.
What do you get for the power in? So let's say you put in, 100 watts, keep the math simple.
Sure.
What do you get out for that 100 watts? Do you get out a millinewton? Or what are you projecting to get out? I don't know if you would get anything yet.
Currently I'm the single beam tests with the 7 before changing it around. I was getting 2 pounds of reverse thrust and 15 pounds of forward thrust. So in effect, we were getting 13 pounds of thrust out of that single beam unit with the timing incorrect and the masses that weren't working as effectively as they should. Pounds to newtons, that's fairly simple math, but yeah.
So what kind of power in to get those 10 pounds of thrust out?
Let's see. If we're running 10 to 15 amps, let's go on the high side, 15 amps at 12 volts. Yeah, we're only running, we're at less than 200 watts of power.
Okay, so what you're telling me is if you turn that thing 90 degrees, put in those 200 watts, it should lift its own weight. Let's say you build it for 9 pounds. The whole thing, 9 pounds.
If it
weighed degrees to the vector, the gravity vector, you put in those 200 watts, that thing is going to leave the ground?
If it was light enough, yes. It's not.
If you built it for 9 pounds and
right.
You have a 10-pound output, according to your calculations, then you're telling me that thing will lift its own weight?
Yes.
When ever are you going to do that amazing thing?
I'm sorry?
I would love to see that.
Is it possible to make it that light and produce that much thrust? Because part of the action mass, is an equation to how much thrust you end up getting.
Right. I mean, you've got to have enough mass to move around to make that amount of thrust. I've tried moving small, light weights at a high rate of speed, and all I ended up doing was destroying bits and pieces of machinery. It didn't like it, not with this design. With the Pi X or the Trammel engine that I am still building, that one runs a lot faster. That one has smaller masses that it's moving. I've seen that one put out over 15 pounds of thrust at 1,000 RPMs.
Okay, so I'm really lost on why a little bit of mass moving really fast isn't the same as a lot of mass moving really slow, because they have the same inertia.
It can be.
They have the same.
It can be, but part of this is the duration of the pulse too. And you're not going to get much duration on a lightweight mass. I mean, everything is relative, so the duration is still only going to be a ratio of its total movement.
Okay, so I kind of forgot about.
And you're also dealing with physical limitations of the materials.
Yeah. So could you switch that over to piezo? I mean, then you could hit a really small, a really small pulse width.
It's
possible. Whatever it is that you need that pulse width for, you could use a piezo to power that.
And then you're getting into Kurt's territory.
Yeah.
Oh, is that
was what I was just
really what he's doing?
That's what he's doing, yeah.
Okay. All right. I got a whole lot more hope for him now. All right, continue, please. Sorry.
Yeah.
Did I mention that there are a lot of?
I'm connecting the dots here for you.
Thank you.
This is the rotational Mega Drive.
This is rotational Mega Drive, yeah.
Okay.
And I have a gyroscope version that I'm in the middle of building. If anyone knows a really good CAD engineer, I could use some help with that. Oh, and Brian, I got a fourth axis set up for the CNC, so we could make some cool.
Speaking of Mega Drive, so Michelle is in just a couple of minutes here. Michelle is queued up. She's going to do if you guys saw this in the open mic, she's going to do a massive walkthrough on her stuff too.
Brian, check this out.
That's awesome.
Yeah, that's this piece alone costs like 15 grand.
Oh yeah. Well, I'm aware of what that machinery does cost. I'm more than well aware. That's why my personal machinery is small manual machines. I have to go and borrow when I need something a little bit bigger and better.
So Brian, your dead blow weights reshape the force time profile, right? Have you compared equal energy but different impulse shape configurations to see whether waveform is more important than the actual total energy of the system?
The shape of it, that's been another point that we've discussed quite a lot in the workshop, because there have been different theories on different shape designs and how they will react. With this particular design, it's not so much the shape as it is the amount of space inside for the dead blow to become effective. So when I had the masses lined up the long way, there was very little room for all that the shot to move around. Now that they're sideways, there's a lot of room for that shot to maneuver, and it lengthens that pulse duration enough that it makes a big difference. It's huge.
Mm-hmm. Brian, are you open to having anyone come visit your lab?
Eventually. Eventually.
I'm driving distance. I would like to stop by when you're open to it.
One of these days I'll be able to do that. Right now, not quite so much, but soon.
That's awesome. Well, and guys, so it's 2:59 Pacific, so we are just about there. So let's do this. Let's put our hands together one more time for Mr. Bryan St. And Brian, thank you. I genuinely cannot thank you enough. I'm overjoyed. This was an amazing presentation. Thank you so much for walking us through it. This past, present, and future. I mean, you went through the whole thing, and it's amazing to see the progress you're making.
Well, thank you for inviting me to do this. Thanks.
Absolutely. Okay, so I'm going to take everybody out of the studio and I'm going to bring in Michelle Broyles. Okay, Michelle, are you with me? Okay, and you're muted, Michelle. Okay, and it may be just a sec because Michelle has been waiting patiently for. Hey, Michelle?
Is this better?
It is better. Wonderful. Wonderful. Thank you so much. So for folks, like, we do the open mic and we're not recording those anymore. You did an absolutely stunning presentation on the Shell-Woodward lab, the work that you're doing, as well as like how that relates to Jim Woodward's work and Curtis Horn's work and like your working group's progress, I guess. You did that like two weeks, a month ago, something like that. And like I have been begging you to do a presentation, so thank you so much. Should I put up the slide deck first, the lab work in the Mega Drive?
Sure, go right ahead. If you want to do it, I can tell you which one to step through, or I can do it.
Yeah, actually, if you want to do it, if you move your mouse over it, it should have back and forward buttons.
There we go.
There we go. Yeah. So let me do this. If it's okay, again, we're live streaming now. I will take myself out. I'll hand things over to you. Let me know. You also have a couple of other slide decks, and it looks like some images too. So just let me know when I can put those up for you.
I have some images, and I actually have. I think you have some videos there too. Anyway, thank you, Tim, for inviting me. Sorry it's been so long since I did the last presentation. I guess it's called being busy. I'm gonna kind of donate this to Jim Woodward. We lost him last August. He had driven this project for approximately 30 years. And in this picture, you can see him grinning like a Cheshire cat. And he knows that what he has done, or he had done, was a real nice piece of physics. And then he matched that to doing something on the bench. So that's what I'm going to cover here. I'm going to cover a little bit of why this thing works the way it does, some bench results and some analysis, and maybe where we're going to end up at. So I'm going to cover some of the basics for the rest of the audience that may not know how the Woodward Mach effect works. Einstein had an idea that inertia relates to the gravitational influence of all the matter in the universe. Everything is connected. And that just makes a lot of common sense. Ernest Mach, who Einstein collaborated with for a long time, said that an object's inertia, specifically its resistance to acceleration, it's not an intrinsic property. It arises from the gravitational interaction of all the mass in the universe. It says that all the mass in the universe influences the mass in the universe and also an object's inertia. Einstein did agree with that. So he incorporated Mach's ideas into the general relativity and considered them central to the theory. And this is what it really boils down to. If inertia is relational and it's linked to all matter everywhere, and it should be possible, and this is what Jim was saying, it should be possible to interact with that cosmic gravitational field by rapidly cycling a body's internal energy. The universe's mass becomes the reaction medium. The picture on the left side of the screen is that device that Jim had an idea of how to build 20 some odd years ago. In the center portion of this, you have a stack of 8 PZT discs, and this is Steiner's Martin's SM111 disc. One end you have an aluminum mass, and the other end you have a brass mass. So you have differential masses. You have asymmetrical masses on the ends of the PCT stack. The PCT stack is compressed, so you set it up so that you're pre-stressing the PCT. Then you drive the PCT. Let me go to the next one. Then you drive the PCT with the signal, a drive signal, at between 30 and 40 kilohertz, and that allows the PCT to breathe, open, and expand all at one time, and then it collapses. So it breathes in and out. As it does so, it interacts with the asymmetrical masses on the end of the device. That's called a mega device. And with that, activating the masses on the end of the device, you initiate Woodward Mach effect. You get a mass fluctuation, and with that mass fluctuation, you get this equation that can derive the acceleration and the change in the power of the device to give you a force. And it's a directional force. And I'll tell you in a little bit later how the directional force comes about. But you want to have how do you do a Woodward Mach effect drive? You extract the net force from periodic mass fluctuation. That's exactly what we just talked about. Then you create a periodic mass fluctuation in that object, which is in the mega drive itself. If you time it just right, you push when the object is more massive, and you pull when it's less massive. So the device breathes with asymmetrical masses on each end of it. From that, you can extract a time average net directional force. And you're interfacing with the universe's gravity field. Now, this is the interesting part. Imagine you're sitting in a canoe on a lake that's calm, and you forgot your oars. If you're sitting in that boat, this canoe, and you want to get to shore, and you can't paddle, you could say, okay, well, then I have to shift back and forth. No amount of shifting back and forth is going to take you in any direction. It's not going to get you closer to shore. It's going to just, the center of mass will stay right there in this, within the same plane as like where his feet are at. So you could shift back and forth all you want. You're not going anywhere. It will only oscillate about the same position. And what's saying is the internal forces alone cannot produce the net translation. It means that you cannot get to shore. And you're going to sit there wishing you brought a fishing pole at least, you know, not going anywhere. So with that in mind, we're going to take a look at the different test facilities that this group has been working with. One was the Fullerton CSUF lab, and that's a vacuum chamber with a horizontal torsion beam, balanced torsion beam, with weights at one end, a C-flex bearings in the center, so it's balanced, and the device at the right-hand end. There is a, at the left-hand end, you have a fiber optic sensor that senses motion and distance. And at the left end, over on the, on the right end, you have a video camera. So you're able to take videos of the device and the torsion arm and cross-correlate what was happening with the laser sensor at the other end. This was in operation for, I don't know, maybe 15, 20 years. So that they would operate the device in vacuum. I took it a different step. Vacuum chambers are quite expensive. And in the last year, a little less than that, I've expanded my lab and set up the lab to incorporate all the stuff I'd been doing before with a frictionless air-bearing system. So, and also design a system that I would not have any stick slip. It was frictionless, and it would negate any issues with slipstick or air movement. This is the old lab before I moved it on over. And I'm going to cover some of the stuff in this because you can see it a little bit better. In the center here, you see the polycarbonate structure here that was set up. You could see a air bearing, which is in the center of that structure. And that air bearing is a frictionless surface. There's no slipstick. It's extraordinarily sensitive. Excuse me. And underneath that is an enclosed drive that sits, which you can see down in the bottom right-hand picture. I enclose the drive in a polycarbonate tube, about 1/4 inch thick. There's acoustic end plates on both ends, but I took the one off so you could actually see inside. Instead of using bearings or anything else, I supported the structure with a poly thread, which is extraordinarily, it's stretchy. It's like the ones that you have in your underwear. And it's suspended in here, and it can freely move back and forth. If there's any kind of air coming out from the device, or it's actually like an air pump, which it does do in a bit, it hits the back wall, and then the tube goes one way, and it cancels it out. So it can also, if it oscillates back and forth, if it's sitting on the air-bearing rod up here, it will cancel it out. Newton's third law says that will cancel it out. So you could actually take and put inside this, you could actually put a asymmetrical rotating mass back and forth, or a coil if you wanted to, and vibrate the coil back and forth. So what you will actually end up doing is you just vibrate this back and forth. The air bearing will compensate for it, and it'll go back and forth, and you'll be like the man in the boat. So you can figure that this device, the Mega Drive that sits over here, and that's the brass colored mass here, it's like the man in the boat. It can oscillate back and forth as much as it wants, but it's not going to go anywhere. The center of mass will still remain the same. On this, you can also see, you can see the instrumentation that I had. We take video of the system, and I post-process it in a piece of software called Tracker that would give me the acceleration, the distance moved, the times, so I could post-process that and see what calculate out what total momentum is. On the left-hand side, it's a driver that I use. It's off-the-shelf driver. It's called a piezo driver. It comes out of Australia. It costs a couple grand, but it'll operate up to like, I think it's like 200 kilohertz. So it's well within running at 20 to 40 kilohertz. It's well within its envelope of operation. You can also see the air here that feeds the system, the air-bearing system. It consumes about a cubic foot of air per minute. It's very low consumption. The tolerances on the air-bearing rod in here are about 5 microns. So there's only about a 5 micron gap between the air-bearing and the center rod, and in this particular case, which is aluminum. Let's go to the next one. Okay, I'm going to show you 2 different runs here on this particular system. On this particular system, you could see on the right-hand side, you could see the optical sensor here that shines off a reflective surface. You could see the spider web. It's actually like a spider web configuration here that sits that little man in the canoe, which is the mega drive. The acoustic damping plates. This bottom shaft here, the black one, is a carbon fiber for weight, carbon fiber tube for weight. And this particular upper one here is, at the time I used the stainless steel shaft through it. I eventually went to the other one, which was aluminum, which was a lot less mass, so it'd make it more sensitive. What we're going to do here is we're going to drive the PZT mass inside this device. We're going to drive the asymmetrical masses, and we're going to let it kind of try to oscillate back and forth. Newton's law says I'm going to move back and forth a little bit back and forth here because you're exciting me. So it does. It oscillates back and forth. If you take a look at the red trace over here on the graph, you could see a little bit of movement, Actually, what this is basically it's dampening on down until you just get into the noise a little bit. At this particular time, I am going to do a frequency sweep of 35 to 40 kilohertz. And I'm going to slowly sweep through that, starting at 35, going up to 40 kilohertz. Nothing happens here. At the bottom here, the bottom on the screen is the amount of time that it runs. If you see that, I ran about 36, 37 seconds for total run time here. I get my initial green pulse, which is the green down here, which is the current. I'm monitoring the current that I'm driving the signal into the PZT. Nothing happens. You see initial pulse loading up the system. And then it just sets nothing until I reach a resonance. When I reach a resonance of the PZT and the end masses, the device starts oscillating, like back and forth. Newton's third law says for every action there's equal and opposite reaction. So what happens is it starts oscillating back and forth because it's sitting on the frictionless bearing. And it says, okay, I will oscillate with Newton's law. For every action, there's an opposite reaction. That's exactly what happens. But like the man on the boat, all of a sudden now, I am changing direction. I am actually gaining forward momentum. I'm actually driving the entire system, in this particular case, away from the optical sensor here. The device still shows Newtonian effects here back and forth, but it's the whole assembly is just accelerating up. Now, also on this, if you'll notice over here on the right-hand side, I centered the entire assembly with a piece of polyester thread, which is stretchy, like it's in your underwear, and set it up so that it would be 28.34 grams per 25.4 millimeters of strength. So I know, and that's very small. That's not a lot of force centering this thing. but I wanted to center it and see if I could push the entire device to the left up toward 11 or 10 o'clock here. And which exactly what it did. As I entered into resonance, the entire the entire assembly accelerated for approximately just about 8 seconds, and then reached the limits of the polyester thread, which was holding it back, and then held for about 2 seconds here, actually a little longer than 2 seconds. For about 5 seconds, it held in position. Now, don't forget, I was sweeping through the frequency here. So it accelerated up, reached the limit of pulling that string tight, and then stayed in position until the sweeping frequency took it out of resonance. And then it started falling back apart. And you can see as the resonance decreased of the device, as the frequency went up out of the resonance mode, and it pretty much stayed there until it all collapsed. Now, at the very end, when the system was powered off, there was no drive signal going to it. There's an impulse here. And we've seen that at Fullerton, and we also seen it here several times. I don't know if it's if the device is actually, as you go out of power, if it hiccups and just gives you an impulse out. But this is purely, this is purely a Newtonian action reaction. So you get a pulse here, and then you can see it decay on down. And there's no thrust in this impulse. Where you get thrust in is in this here, the section here. And that thrust came out to approximately 275 millinewtons. And this wasn't the only time we've measured thrust like this on this system and this device. There's been other times. It's very persnickety, but it can't be done. So that's with using the spider web. So you say, okay, let's take and not use the spider web. Let's take Jim's device, which he's mounted on bearings. Let's go back here and take a look at, here we go. Down at the bottom left here, you can see this device here with the asymmetrical masses on the bottom left. You see the brass, you see the aluminum, you see the stack in between, the black area, and it's sitting on a set of, sitting on bearings. And there's a composite of a Teflon bearing. And it has a coefficient of friction of like 0.02. It's not a lot. Also, to center their device, they have Woodward put springs on that to kind of center that so that it stays in the center and won't drift one way or the other. So I took that entire assembly and I figured out that I could put that entire assembly and close it into that spiderweb's tube structure, mount it here on the bottom, and run it. But what it showed was out of about a 40-second run. It was about the same thing that I just saw in the test I showed before. But I took, excuse me, instead of using just the optical sensor on this one, I'm going to show you where I did with tracker. And this was with the video camera. In the center of the image that you see here, you see a little white target. That's on the outside on the tube. See a little red, it's a little black dot there. And over on the end here, it's hard to see, but there's another target spot over there. So inside of that, that's the device. So I'm monitoring the device, and I'm also monitoring the outside of the tube. And this entire assembly, this tube assembly, is attached to the carbon fiber rod, and that's attached to that air bearing, frictionless air bearing. So in this particular case, I drove it from this particular device, drove it from 28.25 to 28.75 kilohertz at a lot lower voltage, because I was going about 40 seconds. And I post-processed this movement, this motion, within Tracker. So it took those little points and it tracked acceleration, it tracked motion, and the device is in green with the black line, the air bearing, which is the outside over here, which is that a black dot. That's the air bearing. I started the sweep at 0 seconds. Here's one, here's the other. Nothing happens. Nothing happens. I hit resonance. The Q is starting up. So you see the impulse here. And you see nothing happen. It stays the same until it reaches a higher Q. When that happens, you could see the device, which is the green, accelerate down and then start pulling the tube and the air bearing system along with it. And as we approach closer into this system, you can see the device is thrashing around on the bearings. There's a lot of slip stick into this, and you'll get a lot of action reaction. You can actually see that at approximately 24 seconds here. You could see where this line right there going down at 24 seconds. You could see that the device actually just accelerates like crazy going down. But if you take a look at above it, there's the red opposite and actual reaction. So you get the device doing a little bit of slipstick, kicking off the bearings and the rods, kicking one way, and the device kicking the other way. It's basically a cancellation. So it goes back. The rod stays about the same. So you're accelerating here. You're reaching maximum Q, and the device accelerates, and the entire frictionless assembly accelerates down. The device pretty much stays right where it's at. It's running out of resonance. And then at the end here, I'm out, totally out of resonance. The device is staying where it's at. The system is pretty much staying where it's at. On this particular one, I did not use the polyester thread on it. So it's floating by itself, totally frictionless, non-dampened at all. With this particular one, we ended up with about 2.8 millinewtons of thrust. So it still was a positive, even though it wasn't as much of a voltage driving it or not, since I was going such a long period of time. Okay, now for some really heavy stuff. Fullerton, for years, had been relying on the torsion arm, the optical sensor at the end of the torsion arm, to determine where thrust was being made and the deflection of the torsion arm. Well, that deflection could happen on a couple different ways. That deflection could happen on slip stick, could happen with bearing loading and unloading. It could happen with springs compressing and decompressing. It could give you false indications. And we weren't sure whether what we were seeing was giving us good data back. So in 2022, I started doing I did a run. I pulled it back out of our history. The run was done on 12 August of 2022. what I did do, reprocess this on May of 2024. Down at the bottom left of the image, you see Fullerton's, in the one box, you see Fullerton's video and overlay of all their data. The green here is that is the temperature. The red line that you can probably see in here, that's the deflection of the torsion arm through the laser sensor. And the blue is a power, and that's I times E. It's a rectified power curve. So we take a look at that. On the bottom left corner of this picture is the FFT, and that gives you the harmonics of the system. On the right, you have a pi's display. That's power, current, voltage, and stress. So they're monitoring the stress of the stack, they're monitoring the power levels, they're monitoring the phasing of the current and voltage. And you could see on the right of this little box, you could see where we had large deflections of the system here. And that's like, that's interesting. So how does that equate if we turn around and take this another step? And we take a look at just one of these impulses. The green up here is the device. The green trace is the device, because I'm going to post-process using Tracker. I'm going to post-process the video. If you look at the bottom left hand, you'll see a little black dot. You actually see two black dots. One's on the device and one's on the torsion arm. So the device is green. The torsion arm is red, the red trace here. And you can see it over on the left-hand side, red and the green. The line in between all of it is the center of mass. If you know the mass of the device, you know the mass of the torsion arm, you can calculate out center of mass. Let's go back to the guy on the boat. If you remember the guy on the boat, he can rock back and forth all he wants. The center of mass will stay the same. The center of mass should not change. It may increment up a little bit, but it'll go back. So it's going to stay right exactly where it's going to be at. So let's take a look and post-process it a little bit more. Let's take a look at total momentum, which is different than the center of mass. Total momentum is, okay, I know the mass of the device. I know the mass of the torsion arm assembly. I can take that, I can put that in the equation. I know the compressibility of the springs. I can take that into the equation. I know the compressibility of C-flex bearings that support the torsion arm. I can take that into effect. I know the coefficient of friction of the bearings that this device rides on and the shaft it rides on. I can take that into effect. That's like 0.02. So I've taken every motion, every friction, every spring compression into account and calculated out total momentum. And that can get us as close as we can to force calculations as possible, which is the dark blue line on this. If you can see the dark blue line on here, you can see it, that it jumps up back and forth quite a bit. And initially we thought that the force was on this solid projecting green line, the device, which is this red line up here, the red line, which is going from 36.5 to just about 38 seconds. If you see the timeline on the bottom, we thought that was the force. We thought that the device was driving down and here's our force. We were wrong. That's not where the force was coming from. It totally flipped our idea of where the device was resonating and what was happening when we calculated out the total momentum. So when we calculated out the total momentum, we come up with some interesting numbers. If we take an average smooth momentum, so we take out the noise and stuff of the system, with average smooth momentum, we came out with a force that was in the Newton range. Actually came out to approximately 8 newtons. And that's the line that you could see that's above this peak line of 8.76 newtons. You can actually see the little dippity-doo right below it, and that's at 38.5 seconds. So at peaks here, even average, we were seeing of this system, and under like ideal systems, trying to account for every mass, every spring, every coefficient of friction and within the system, we were seeing and calculated out large Newtonian forces, large Newton forces. This was a surprise. This was a good verification beyond what the Woodward group had been doing at Cal State. So what is doing this in 2 different labs, 2 different support systems as far as the device, one on a torsion arm, one on an air-bearing frictionless system, one encapsulated with bearings and slipstick, still able to account for that. Another one with no slipstick, no friction, and an enclosed environment. And being able to, with both of those, being able to see a measured thrust. It says it can be measured in quantified multiple ways. So the Woodward Shell Lab here re-verified what Woodward was doing in California in his lab. And the forces are different. And they're different because I didn't drive them as hard, or they were driven like a different signal, so on and so forth. But they all went, they started at like approximately 3 millinewton all the way up over 8 newton peaks. So it's saying that, yes, there is something there. So this is, like I said, this was dedicated to Jim. This is why we all continue to do our work. This is why Curtis is continuing his, and Paul March is still doing consulting work, and we have several others on the team that contribute. And this picture of Jim is one of my favorites, other than the one that that was taken at the beginning here. This was this was Moonshot, and it was it's on YouTube. You can type in 2 scientists are building a real Star Trek impulse engine. You can actually see an interview. It's called Moonshot. It's by Bloomberg TV, and it's a nice overview. It gives a good explanation of why this works, why it works as it does. And so here's some foundational papers. Some of the stuff that we've been cited in, like Scientific American, they've written about us. Multiple publications, papers over the years. And I know I'm going to be leaving early, but I'd like to thank everybody for inviting me. And hope you enjoyed it.
Hey, Michelle?
Yes.
Okay, sorry about that. I did not have my headphones in. Do you want me to put up? So we have a couple. Let me put these up.
All right.
Let me see. So I'll put that one up first. This
Oh,
is
yeah.
the float your stack.
Let's pop it up.
Yeah. So I wanted to put that one up. And do you think you could tell us about that one? It's no ears, 8 stack, 30 to 40 kilohertz.
Yes.
Yeah.
I definitely can tell you about that. On this particular, what you see here is a slide. I did a interactive frequency and phase on an FFT model. Some of the critical things for driving this device is the harmonics of the device. So when you take the PCT stack and you cause it to breathe in and out, you got a light mass on one end, you got a heavy mass at the other. It breathes in and out, and it puts force down through the PCT stack that's breathing in and out. And that force that it puts down through it will actually create your second order, third order harmonics of the system, of the device. Normal Newtonian mechanics says if I breathe in and out here and I go back and forth and so on and so forth, I'm not going to go anywhere. I'm just going to sit here and go in and out. But under certain conditions, when you compress the stack and you get the right phasing of especially the second order harmonics, what happens is second order harmonics and fourth order harmonics are 180 degrees out of the primary incoming signal. So that being 188 degrees out, they cancel out and they give you a DC value. That DC value kicks up and that gives you a directional force value. That's where the device is not operating under normal Newtonian, where it's not operating under normal Newtonian. You amplify signals at a particular time, and then you get a directional force. What wasn't done for years is to be able to take a look over a frequency scan and saying, where are my harmonics at? And let's take a look. The white line down here at the bottom is the primary drive. That's the signal coming in. The next one up is your H3, or which is your third order harmonic. That's a nasty one. That appears when you don't want it to. When that shows up, you kill your device. It basically turns, it generates a lot of heat. It kills your signal. If you take a look at the blue one, next one up, that's your second order harmonic. That's a critical item. You take a look at the next one up, which is the green line. That's the fourth order harmonic. So between the green and the blue are your critical go-to harmonics that you need the system to generate. And we're actually monitoring the current. This is the current driving into the device that gives us the harmonics out. So we're monitoring what the device is actually generating internally. And when we generate just the right amount of force, when we get it just right, we end up with what you see here in the vertical dotted line right here. You see here, and the pink with a red dashed, that's what's calculated out, saying, okay, the third harmonics is the minimum that we can get. The second and fourth order harmonics are peaked. This is the maximum thrust point out there. And in relation to the other resonant frequencies down here, you got one around 35 kilohertz. This one's up around 38 kilohertz. Actually 37 point something kilohertz. And actually it's 37.427 kilohertz. That gives us a real pinpoint area where the harmonics peak and we get, excuse me, and we get maximum thrust out. That will allow us to turn around. Oh, incidentally, when we get at this particular point, this is high Q. We're not dissipating a lot of energy under third order harmonics. The power levels drop down to less than 2 watts. In some cases, between 1 and 2 watts. The device is generating your harmonics, it's generating your thrust, and that's at that particular point at 37.427 kilohertz. The other critical thing is that I'm also monitored, which was the phase between current and voltage. That was also a determining factor of where you get your maximum thrust. So on the next test, instead of sweeping into this arena right here, instead of going and sweeping from like what they used to do, like they go from 35 kilohertz up to 40, or they go from 30 to 40 kilohertz, and you sweep real fast through this whole conglomerate, and the device creates all these harmonics up and down. By the time you go through that real narrow frequency spectrum, and you can see it here, it's not very wide right here. It's about 100 to 200 hertz wide. If you're sweeping real fast through that, of course you get what they call DP over DT. You get a significant thrust impulse out of that jerk action. You get that out of that, but it only happens so quickly that you can't equate that out into a real thrust figure. It gets dampened out through the system. It's a shock through the system. So the next step is what we're going to do is I'm going to take this particular frequencies, and I'm going to also gain dP over dt. I'm also going to gain that big impulse. I'm going to take the signal, which is normally just a sinusoidal signal that's frequency sweeps. I'm just going to set it at that particular frequency. I'm going to do an AM modulated waveform. I'm going to impulse stop, impulse stop, impulse stop, impulse stop. So I'm truly going to be going to an impulse engine at one particular frequency. And since I'm not consuming a lot of power here, the drive is not going to drift. So impulse, 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 impulse. This is the next step I've been working on for like the last 2 weeks.
Oh, so wonderful, wonderful. Now, Michelle, you have one more as well. If it's okay, let me put this one up. This is Millier's 4 ounce.
This is a different. Yes, this is a different stack. This is a different stack. I took the old stack out, that's what you saw on the one previously, and I put a new stack, a PZT stack in it, just to show the difference in the two stacks. Now, this particular one, I show the higher drive frequencies, but at the lower drive frequencies, which is actually the electrical resonance, I show very little activity. If there is any activity, like down around 32 kilohertz, you can see the third order harmonic, which is the H3 over H1 right here, is really high. That means that, yeah, it's not working really well. Even though the phase shifted in like it was supposed to, there was not a lot of force being generated by the PZT. Until I got up, until it excited this is a different stack now. Until I excited the motion of the end masses and stuff. Now I see right around 36 kilohertz or so, some activity on the green and blue trace, which is the H2 and H4 harmonic, which is the even harmonics. But at the same time, I still see a lot of the H3, which is the, I guess you call that kind of orange. Depends on your monitor. So you see some of the orange. This device, there's a very good chance that it would not produce a lot of thrust. So what I have been doing, Jim sent me a whole box of PZT stacks. He said, these are all dead Indians. And I have been going through that box, and I've either been able to resurrect them or just put them over into another box because they're DOA. I've got a couple out of there that are, one is really good and the other one is kind of marginal, and I'm still going through them. Would you like to show the video? The video?
Okay, there we go. Sorry about that. Let me click play, and we'll cross our fingers. There we go.
Okay. We could stop this here. Go back to the beginning, and I'll do a descriptor. Okay, this was some of the work that I did. I think it was 04, 05. That what we're looking at the video camera into the vacuum chamber of the device, which is on the, it's got the yellow tubes here. That's just covering the screws. And the little wiring here, back and forth, each one of those is a PCT disc, and there's 8 of them. You've got the asymmetrical mass over here on the right-hand side. You can see it in the brass colored here. You can see the device riding on a set of bearings and springs. On the right-hand side, you can actually see a target here. They put this block right here attaches right to the torsion arm. So the device is riding back and forth on the bearings, on the rods. And what we did is we tracked it. We tracked this target here on the torsion arm, which is the big black blob right here. And over here on the device, you can actually see another block underneath all the little red, white, and green, or excuse me, red, blue, and green tracker artifacts. Over on the right-hand side, what that equates out to is the green is the device. That's the device here with a yellow line, yellow shrink tubing, by the way. You can see the device, and you can see how it climbs up because we're tracking it. It's moving. And tracker gives you acceleration, and it gives you distance. The red is the torsion arm. Initially, when this thing starts off, you get a slip-stick reaction where the device goes one direction, the torsion arm goes the other way. But what really happens is when after that slip-stick, and what happens is that means that third order harmonic kicked in and it engaged onto the bearings a little bit. So one kicked one way, one kicked the other way. And what happens is at the end of that, the device is still moving and still pushing. And it starts pushing the whole torsion arm. And this lasts for like a good second. So if you play the video, Tim, what you'll see is the device wiggling around a little bit like you see here. You see the device shove right up into the torsion arm and hold it for a second. Boom, there we go, pushing everything right there. I'll play it again. And this is through a frequency sweep, so you're only going to have a thrust for a certain amount of time. And there we go.
Awesome. Thank you.
You have another one?
You do have one more video. Do you want me to put that one up?
Sure.
Okay. So we will do that.
Okay, so let's go over and take
all of our media.
Yeah. So let's go over and take a look from Fullerton, University of Southern California, and let's take a look at my lab here. Now, I took that same assembly, not the same, but it was a similar assembly, put it in a sealed environment. No air, actually air cannot really get in and out of this system. So if the device pumps air a little bit, it's negated. And on this particular one, you can actually see, the carbon fiber tube that I like this image. You can see the carbon fiber tube that this entire assembly is attached to. This was all done for weight. Keep the weight as light as possible. Who wants to try to move a heavy mass and try to measure it? That's why the bar up here is black. That's aluminum now. I went to an aluminum bar that goes through the air bearing. It's in the center of the air bearing. So what will happen is you'll be able to see the device go one way, dink, 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 and then accelerate. And you can see here the actual motions of the device. And this was a sweeping frequency. So you go ahead and play it.
There we go. Okay.
Yeah. There we go. Acceleration.
That is amazing. Absolutely amazing.
Now, the interesting thing is you take a look at about 33 seconds. That's where we met resonance, 33 and about 55, and over here at around 80. You notice that the blue trace, which is the center of mass, if the center of mass should never deviate, it should look like the first one here that you see at 22 seconds. It should stay. It should not jump away. So you can actually see the device moving and accelerating the entire system in one direction through a frequency sweep. So I thought everybody liked to see what I was doing with Jim's device in a sealed environment.
Okay, and let me see. I'm fast forwarding through it. That way we can kind of see.
Okay.
Yeah, because the motion isn't that fast on this one. So there we go.
Now,
Michelle, that's wonderful.
The thing is on this is by doing frequency sweeps, boom, 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 you cause the device to go in resonance and out, in resonance and out. And if you have a spring, or if you have like a torsion arm, which has the C-flex bearings, which are centering springs, if you have any of that to center that, what you end up is you get impulses, and you have to turn around and you have to derive where is the total mass of the system, total mass of your air bearing system, total mass of the torsion arm, total mass of everything. It's a lot easier to get a full linear motion where, where I can take a signal, I don't have to sweep it, then I can impulse it, stay at the same frequency, and then accelerate so that I can take this and I can accelerate, hold it down, hold it in position, which you could see I did at a slow sweep rate back in the middle of my presentation, where I held it for, or you can see where the device accelerated up and then held the entire system. But that was a very slow sweep. That, I think I was like at 10 hertz a second. So by slowing it all down, I'll be able to get a directional force that can be attributed to thrust.
Amazing, amazing. So Michelle, let me take that one down. And what I want to do is bring everybody in. We absolutely need to give you a giant applause. Michelle Broyles, thank you so much. Michelle, thank you. I truly am honored to be able to have you with us to talk about the work that you have been doing. And actually, Curtis is here also, and you are working alongside Curtis. You guys are partners. And again, I cannot thank you enough. I mean, the work that you guys are doing, it is so scientifically rigorous. It is detailed. You have an amazing team that is built, and you guys are really doing this the right way. And that's, I think that is so important. And so the results that you guys are getting, these are valid results, right? This is not, it's not scientific error, it's not noise, it's not this, it's not that. You guys are doing the hard work and you're doing it the right way. And it is absolutely amazing.
Well, the thing that drew me through this group a little over 5 years ago, I met Jim back in 2016 at the Estes Part propellantless systems. And I was impressed with one thing, and that not only did Jim have a device, but he also had a theory behind it. I think with a lot of the systems that we see out there, you have the device, no theory, or you have theory and no device. And the two have to complement each other. They may not agree 100% of the time, but if you can work it out, you can get to the point where you can take theory, match the results from your test bed setups, and then you can amplify and get better results in a better device. And that's why I'm glad Curtis is on board here and he's doing his work. That extends what Jim was doing. So we're just kind of glad to present what we're doing to the group here.
It's wonderful. It's wonderful. Okay, well, so it is the top of the hour. Do you guys have questions for Michelle at all? Does anyone have questions? Drew, go for it, sir.
When you're operating in the kilohertz range, what's the frequency at which you're taking your data samples? Are you also in the high kilohertz range for the data logging?
Okay, there's two different ways. In the video, I have a camera, and that's every frame, and it depends on the FPS of the camera. With a video that was taken by Woodward, it's at 55 FPS. The one I did, it was at 30 FPS. The other data is from the optical sensor, and that's in the microsecond range. It's like 2 microseconds or so. So it's a lot higher resolution.
So 2 microseconds is 2 millionths of a second?
Yes.
So you're recording 2 million data points every...
No, it's 1,000. 2,000ths of a second. You said microsecond or millisecond?
Micro. Not
that's, you're right,
micro.
to 1 million, yeah.
So you're recording
500 kilohertz.
Million samples a second. Yes.
You're recording 500,000 frames a second?
Not frames a second. If I'm doing video and I'm post-processing...
Your data set. You're recording...
2 different ways, Drew. One I do it and I compare both. One I do it with the video, and that every frame of the video runs in either 30 FPS frames per second or 60. The other one is through a Filtech optical sensor, and you can actually set the data sample rate with that, but that's usually up in the millions of samples a second. So.
And what does that optical sensor feed? What part of your giant data set does that optical thing feed?
What giant optical? That shows the deflection.
You had a whole lot of lines
that shows
on the
either. Oh yeah, that shows the deflection of the entire assembly.
And that's the distance from a fixed point.
Yes, thank you.
Okay. The reason I mention this is because we operate around 250 hertz for our sampling rate, and that's fine because we have a static system, so we don't have any impulse. But the second we went into we were like hitting it with harmonics, we were hitting it with pulses, trying to get into resonance early on because we needed more. We just couldn't see the thrust because it was so low, and it didn't take much for the data collection output, for the data to unsync with reality. Whereas, we would be on our way up for a pulse, and we'd take a snapshot, and we'd see some value, and then we'd be on our way down from that same oscillation, and we would take another value, and it almost instantly decoupled with reality. I mean, we were seeing, Newton thrust levels.
Sure.
Because we were taking snapshots out of sequence of reality of what the thing was actually doing. But that's what our fixed data rate was going at. That's why I was curious of what your average data rate is. But if you're saying you're up in the millions of cycles, 500,000 cycles a second.
That would happen, Drew. That would happen whether that's just your sample. Okay, I'm going to take a digital photograph of where the position of my arm is, or where the position of my assembly is at. Boom! I'm going to take a picture of that. That's what your D to A does, and then it converts that into a number. You wait for a specific period of time. Boom! Take another picture. That period between the first and the second, the differences between the peak values between A and B, it's going to be the same whether you sample a lot or whether you sample one and the next and the next. So the key here I found is when we took and did a video of it. Now our sample rate is frames per second. It's not the video isn't touching anything, so I monitor a target, and the resolution of the tracker software is going to depend on how good the camera is, but it's normally around 5 microns. So that's very, very good. Tracker does a wonderful job at determining exactly where a position was. So
that's great, but it's only analyzing the finished frame. If your finished frame, you know exactly what's where in that frame. But if the frame is unsynced with reality, it doesn't matter how good the analysis of the frame is. So the point is, I've worked with NASA a lot on their telemetry. They do a 10-to-1 ratio. So whatever they're analyzing, whatever sequence they want to record, the data recorders are running at 10 times that speed. So if they're expecting to see 100 hertz, something move at 100 hertz, then they're recording at 1,000 hertz minimum. 1,000, they're pulling 1,000 data sets a second. So I was just wondering, are you operating at 10 times your expected data rate?
Now, it's not the data rate so much as 10 times the expected motion.
Right. Are you operating at 10 times your expected motion?
Oh, even with the video we are.
So I hate to interrupt, but Mark is on a deadline today. I need to get Mark to upload his presentation because he is going to do a lab update. And I should apologize for kind of cutting things short. We're about 4 minutes over the top of the hour. Because Mark only has a few minutes. So if it's okay, why don't we do this? Mark, why don't we start uploading? And
it's uploading, yeah.
Yeah, let me ask you, please put your hands together one more time for Michelle Broyles. Michelle, thank you so much. Thank you so much. And I'm sorry for cutting things short. We had extra time at the beginning, and now we're running a little tight. So.
Sorry, Tim. I can be.
No, not at all.
I tried to hurry a lot.
No, not at all. It was absolutely wonderful. And I'm truly honored to be able to have you with us today. I mean, this is, I think, one of our best APEC conference sessions ever. I'm so excited.
Yeah, I would like to hear more from Michelle about her waveguide contraption that destroyed the test stand.
I'm working on that. Mark, hang on. I'm working on that. It's not ready for public release yet. There's a lot of work to do on that. And the stuff I'm doing also with the Mega and the phases, as far as the harmonics, are critical to the other tests that I'm building right now. So the two cross correlate. So it's a lot easier for me to get data out of what I'm doing right now, with like the Mega Drive and analyzing the harmonics and stuff like that, where the actual thrust comes from. And I'm going to apply that back to my other device.
Awesome.
And like I said, I'm not ready to release all of that quite yet, but
Well,
it's
I
coming.
hope you come back and give us a presentation on it, because that sounded really excited when I first heard about it.
Oh, yeah.
Oh, yeah, I will do that.
So yeah, if it's okay, let me do this. I'm going to take everybody out, and again, let me apologize. So I'm going to take, and then Mark is going to do, I guess, kind of a lab update, right? So
This is a lab update. This is the same presentation I gave at Deep Tech Week New York, and I added some new stuff into it. So Tim came down this past weekend, and we had a little get together here in the city. It was hosted by Morgan Stanley, and Charlie Bueller was there, as well as Sonny White, Eric Weinstein, and Max, a theory guy who lives over here in New York City. And this is basically the presentation I was giving. And I just added a few slides right now just to give you guys some more updates and stuff that happened in the last week. So Falcon Space, anti-gravity with present technology. This is an overview of the Alzafon effect. Many of you might have seen it before, but we will dive into it again anyways. This is the only experiment that I know of after all these years of APEC that can actually be called anti-gravity. And we'll explain why in a moment. So science says that faster than light travel, space travel, is impossible. And there's two reasons why. One is getting up to the speed of light, you have relativistic effects. You have energy and mass equivalence. The mass becomes energy, and the energy, then you need more energy to move the mass, and it becomes the mass to energy equivalence ratio is dependent on the speed of light. It is the speed of light, actually. So the closer you get to the speed of light, the more the mass of the object becomes the weight of the entire universe. So it's pretty much impossible to breach the speed of light because of that equation. And then you have a much more real, even 1% of the speed of light is barely possible because of the rocket equation, which says that your delta V is going to be equal to the equation is basically the mass that you eject times the mass that you want to keep moving in the new direction, the speed that it goes out, and that's basically how a rocket works. So what do these two things have in common? Both of them have this pesky thing called M, mass. Now, so let's concentrate on the core of the problem. It's mass. So on the origins of mass, the strong nuclear binding energy accounts for 99% of it. That's what holds the protons and neutrons together, the gluons, you might call it, inside the core of the atom. That holds all that together, and that is most of the mass. The Higgs mechanism is a small amount. Relativistic energy, meaning how quickly it's moving in relation to you, is almost negligible. Gravitational effect proportional to the total mass energy. So the amount of gravity that it has is proportional to all of those energies combined. But for all intents and purposes, the strong nuclear binding energy is really where it's all at. So let's look into the strong nuclear binding energy and what we can do with that. So we have a process called dynamic nuclear polarization. It was discovered in 1953. Basically, the World War II radar systems were coming back. We had different microwave systems that were used for radar detection of enemy warships. Of course, we had to go to war in order to develop all this stuff. And now they're coming back. We got lots of surplus. People start playing around with microwave generators and spectrum analyzers and all the ancillary equipment that come with microwaves. And they discovered that, hey, it's possible to resonate with electrons. And when you resonate just right, when you have a magnetic field and just the right ratio of magnetic field to microwave frequency, that we call a gyromagnetic ratio, because it's spinning around, or that's the microwaves is gyrating, and then there's the magnetic field strength. When you have the right gyromagnetic ratio, the absorption goes up or goes down depending on the material and how the electrons respond. That is in essence what electron spin resonance is. Now, what they discovered is that it is possible with tickling the electrons just right to transfer orientation into the core of the atom. And this is called dynamic nuclear polarization. We're talking about orienting the protons and the neutron spins. Now, don't forget the gluon energy, that strong nuclear energy that we talked about before, the strong nuclear binding energy, which is mass, is now being affected. So we found a way to use electromagnetic radiation or microwaves along with a magnetic field to orient the strong force, which is the strong nuclear binding energy. So spin orientation alters the way the strong force interacts with the quantum vacuum along the plane and axis of rotation. So the gyroscope kind of moves like this. Just like a gyroscope, along the plane and axes of rotation, the mass is changed. The relativistic mass, the amount of mass that is seeing inertia. One way to think of it is equals mc squared. So mass and energy are equivalent. Subatomic particles, think of them as electromagnetic energy spun in on itself. Now, when you have something spinning like this little saucer thingy over there, it likes to move like this. It moves to move along its plane and along its axis. It can go straight up and straight down. The one thing it can't do is a barrel roll. If you try to change its orientation, it will start to wobble around and do motions like this. Now, subatomic particles are wobbling around in many different directions simultaneously. So here we got one wobble, and then we add another wobble to it, and then you could add a third wobble, and it gets very difficult to do with your hand, but you can get what I'm trying to get at. So if you were to imagine a ball of a whole bunch of these gyroscopes wobbling in many different directions simultaneously, try to move them through space, the spin wobbles would change. And that is what we experience as inertia. So when you take an object and you throw it, and you impart a few joules of energy into that baseball, let's say, all you're really doing is changing the spin wobbles of the subatomic particles of every atom that makes up that object. And that's how it gets its inertia. So how do you get rid of that? Actually, to take that one step further, a rocket engine expels mass out one side. So it's basically trading the spin wobbles of the exhaust for the spin wobbles of the craft. So the spin wobbles of the entire system, it equates to zero. For every motion, there's an equal and opposite reaction. So that's kind of how that works. So how do you get rid of that? You orient the spins. So if all the spins are oriented, same amount of energy is actually there, but now along the plane and along the axes, there's no way to couple to those wobbles, right? Because it's just like a flat gyroscope. You're not gonna change the wobbles if there are no wobbles. And that's why a flying saucer kind of flies like that. It can do a 90-degree turn at 10,000 miles an hour. It can shoot straight up, but it can't do a barrel roll. In fact, many sightings are of it slowly changing its orientation. Another way to look at it, and this was the Alzafon theory, was that it's actually a direct interaction between gravity. I'll get to that in a moment, though. So when this effect was first discovered, it was back in 1953. He ran some experiments. He noticed that there is a thermal part of the equation. The higher the temperature, the faster the spin decay happens. So it's and the lower the temperature, it lasts longer. So obviously, given the funding that they had and the opportunities that they had, they took it down to liquid helium temperatures and discovered liquid helium is like 4 degrees Kelvin and below. Even at extremely low temperatures near 0 Kelvin, the spin relaxation was still happening 100 times faster than that predicted by theory. An important relaxation mechanism has been overlooked. This was what Albert Overhauser, the discoverer of this effect, discovered. And he hasn't published any papers describing what that relaxation method was. Came along this physicist, Frederick Alzafon, who studied relativity under Robert Lenzing, one of the main disciples of Einstein. So he was a top-tier physicist. He theorized that it was gravity acting upon the sample to disorient it. So if gravity, which is made up of, which comes from the Earth, at least over here, the strongest source of gravity right now is the Earth. Gravity is acting upon a sample, and gravity is made up of spin disoriented material, and you have spin oriented material. So if there's a direct interaction there, it's happening from gravity. Maintaining the spin orientation would mean that gravity is now trying to do work on it. It can't, and since it has to do work on it, it's anti-gravity. Now, when he filed this paper, he also filed for a patent. The patent was denied on national security grounds. Now, I'll just give you the backstory of how he even got to this. It's kind of interesting. The physicist, Frederick Alsvan, and his two kids, David and Daniel, and his wife, they were driving and they saw a flying saucer or some sort of a spacecraft that was of otherworldly of some sort. And okay, so now they know that it's real. Then they saw it, it's real. David was in a used bookstore. He found a book by James McCampbell called Ufology, and in page 108, it describes an interaction that a predecessor of an AWACS plane had with a flying saucer. Basically, they saw a saucer that was in close proximity, and it was pulsing 3 gigahertz pulses every 5 milliseconds, and very specific pulse durations and pulse lengths and pulse strength. He brought that to his father. This was supposed to be part of Project Blue Book, but it was removed because it's empirical data, and they didn't want that to give out anything real in Project Blue Book because it was just a cover-up. And his father looked at it and it struck a bell. He thought, this is kind of something like I've seen before. He went into the technical library at UC Berkeley, I believe, and a book, the only book ever written on the subject, Dynamic Nuclear Orientation by C.D. Jeffries, fell off the shelf in front of him onto the floor. Now, as amazing as that is, in 2026, there is only one book ever written on dynamic nuclear orientation. That should be mind-boggling. The fact that there's an entire area of science, a mechanism of orienting the strong force, and there's only one book written on it, just blows my mind. If you go into NMR books, you'll see tons of them. If you look at Casimir cavities, most obscure parts of science, there's lots of books written on them. And this is one book, and it was part of a inner science. It was kind of like a little encyclopedia of interesting parts of science. It wasn't really a standalone book in and of itself, and it's quoted heavily in the field. Now, one of the main uses of dynamic nuclear polarization is to increase NMR's signal to noise ratio. So if you are trying to get an NMR signal back and figure out what a sample is, you're able to use dynamic nuclear polarization of different forms in order to increase the NMR and actually get a signal back. Because NMR is a pretty weak technique on its own. So this is our replication attempts. I started doing this. I had a hybrid battery business. I was refurbishing hybrid batteries at the time. When I got into this, you could see hybrid batteries in the back over there. And I started building these different test rigs. We started seeing things happening. It was exciting. It was interesting. And intuitively, I believed in my core that there's got to be something to this. It seems like a fundamental force of nature, and it's probably been overlooked. So these are, and then as we got funding, we started getting more into it, got better equipment. We got klystrons, we got large electromagnets, started to get more organized. Here we are, we mapped out the magnetic field of this electromagnet that we picked up. And you can see the different strengths of the magnetic field. Red is weaker, yellow is higher. So there was a problem. We had to get a more laminar field so that everything is, the entire sample's in the same strength. We made a magnetic lens. That's what this is, machined it, and it fixed that problem. Here's more iterations of the experiment. We got a Faraday cage in, started running the experiments in the Faraday cage. Turns out the reason why people used to wear tinfoil hats working these experiments, it's because it's basic PPE. So when they're making fun of tinfoil hat conspiracy theorists, in reality, they were making fun of the people who are doing the real work, playing with microwaves, who should be wearing tinfoil hats or silver foil. Actual silver coated mesh is very good. The fact that people go up onto radio towers without any protection is mind-boggling. There's no reason for us to be doing that. And then we hooked up the entire system to a lab view setup. I used to be turning knobs manually to change magnetic fields. It started to get tedious. I thought I saw something happening, but I wasn't sure what. And there was too much human factor involved. So I worked with a programmer in Pakistan, got it all programmed up, and started running the thing with our current setup, our setup at the time, which is in the X band or 9.88 gigahertz. And these are the results we got. We saw a very clear signal. And we wrote a paper on it. David Chester helped me compute the data. Michael Perrone helped me write a critique. So that'll be accepted a little bit more. And you can see these are several runs, and we're measuring the weight of the sample. And you're seeing a change in weight that happened right around that gyromagnetic ratio. Don't forget, that's the ratio between a magnetic field and microwaves, or the gyroscope, the spin of the electrons, the wobbles of them. So that looked very promising. We presented it at a conference, and it was meteorically accepted. We're going to be going to another conference. I'll get to that in a moment. Then I found this other paper, and it talked about a 250,000 time increase in the effect if you use something called triplet state dynamic nuclear polarization. So what this is essentially using the effects of light and fluorescence in conjunction with microwaves to increase the coupling between the electrons and the nucleus. So essentially you have a singlet electron, which is like a ground state, a doublet electron pair. These are pairs. And then you have the triplet state. The triplet state is not a natural state. It's a high energy state. It needs to be something needs to be energized into the triplet state for that to happen. A lot of things create triplet states. If you shine a light on fluorescent objects, some of them create triplet states. And when the two electrons are in the triplet state, they're kind of like floating around in the same orbital, facing the same direction. It's a case of 1 + 1 = 100. Because the amount of magnetic moment that is given to couple from the electrons to the protons or to the nucleus goes up exponentially when you have this triplet state. So using light in conjunction with microwaves can increase the effects of dynamic nuclear polarization. That's what we learned from this. So we've been upgrading our setup right now. On the top left corner, you can see that's a Bridgman crystal growing machine. We're using that to grow crystals. In fact, it's in the other room right now running as I speak. And then in the center, we have the laser light that we've included. We've got a massive laser. It can put out different colors of light. It's actually tunable, which is really cool. And then you have some of the early crystals that we tried growing. We had problems with oxidation, so we're doing a new batch, running it under an argon atmosphere, so we won't have those problems. Another thing that I recently discovered, so this is a new slide. These are called NV diamonds, or nitrogen vacancy diamonds. So I actually have some over here. So these are regular nitrogen diamonds, so they're like yellowish. You see these as these are lab grown, and they have nitrogen thrown into them. So the nitrogen makes the diamond yellow, but if you then create vacancies in the diamond, you stick it inside of a particle accelerator, like an electron beam, and then anneal it so that the vacancy and the nitrogen match up, the color changes and it becomes sort of like reddish blood color. Now, when this is excited with a green laser light, it actually starts to glow red. Now, it's kind of difficult to see on the camera there, but you can see a little bit of the red. And yeah, you see a little bit of red there. It's mostly green that's reflecting back, but there is a bit of red there. That red is coming from the green light being downgraded to red. And in the process, it's making that triplet state. Now, one of the great things about the nitrogen vacancy diamond that we found out recently is that the spin polarization might happen to a very high degree on pentacene on these crystals that we're growing. The problem is the high degree of spin orientation happens on a hydrogen atom. Hydrogen doesn't weigh much, so if we're trying to spin orient a heavier atom like carbon, for instance, this is the way to go, and we should see a much bigger weight change. So we're in the process of getting a much larger nitrogen vacancy diamond. This was just a test run from a guy who has actually drove over here to hand deliver it. He was very excited about it. One of the other uses of nitrogen vacancy diamonds is because when they undergo their spin orientation, when you hit the gyromagnetic ratio of the nitrogen vacancy diamond, it stops fluorescing. So this is used on in many different processes. We're in fact finding new uses for this all the time, where you can put little pieces of diamond like these ones, like little powdered diamond, onto a surface that has a weak magnetic field, and you sweep the frequency. So you start off in the kilohertz and you go up to a megahertz, and like you're looking for really weak magnetic fields, and just keep on shining green light or whatever light on it and watch for the changes in the fluorescence. So as the fluorescence changes, you know, hey, that there's X whatever strength magnetic field based on the frequency. So you're able to sweep frequency and see magnetic field changes. So that's called quantum magnetic field mapping or sensing. So this is our current setup. It's actually right behind me. These are pictures that we just took. This is how the sample enters the chamber. There's a little scale on it, a 10-gram scale, but it's offset from the fulcrum a little bit. So 1 gram is about 2 grams maxes out the scale because it's out on a distance. So it's a pretty accurate scale. We're able to see down into the milligrams with it. And the sample hangs off of a borosilicate rod, so there's nothing touching it. So this is one of our possible next steps that we can do. Thinking about building a device where the magnetic field and the microwaves are all encapsulated in one thing, so we can test the entire weight of the device with the magnetic field on board, so that we wouldn't have to be measuring something inside of a magnetic field where there could be other confounding factors that would make something lose weight, such as changes in its magnetic properties. Another thing that we're doing, I just signed up to join the NMR conference in Washington, D.C. And ever since I signed up, the conference has been converted into a UFO festival. I kid you not, these are the posters that they started putting out for a serious NMR conference. They have been watching me on X for a while, so they know already what my presentation is going to be about. But you can see there's a UFO that is looks like it's abducting a cow over there, and that is their posters for the Panic NMR conference. It's going to be right outside of Washington, D.C. We're going to try to get some lawmakers over and try to explain to them the science behind UFOs. And if anyone can join, it's May 4th to the 8th. And on the 8th, actually, I believe is Stephen Greer's, he has a sphere or something that he thinks is, so I'm going to be there. So I'm just going to go to that. These are other projects that we have going on. We have an electrostatic field generator. Charlie Buehler came to the lab. He saw our latest version of it. He made some recommendations on how to make it better. We're going to implement those, and we are going to put together a really cool experiment with that. I have high hopes for it. He was very excited. He said that the military was given like a couple $1 million and they couldn't replicate it properly. They were just using the wrong technique. We used plastic Kinects. It's like a Tinker Toy kind of thing, like Lego. And as you can see, most of the space in it is empty space. It's not like Lego is a lot more dense. These are just sticks and rods that you connect together, and it's the perfect building material for a project like this because it's completely modifiable. You could modify everything, and it is lightweight, cheap, and electrostatically inert, which is the most important part. In the center over here, we have the Podkletnov gravity impulse experiment, and we have the T.T. Brown replication over there on the right. And here's some of our gyroscopes. So we have gyroscopes galore. On the left, we have the Ford gyro version. In the middle, we have the Gamble version. And on the right, we have, it's a modified version of that. There's also this Ford, it was kind of like a gyroscope, Ted Pittman inspired this device, and it kind of all wobbles together. And over here we have the heavy liquid spinning device. We can spin heavy liquids around. That we're in the middle of a project with the gyroscopes. We're trying to get, instead of an even number, we want to get an odd number of gyroscopes wobbling forward, kind of like that. If you imagine 3 gyroscopes, kind of like, so if there was a gyroscope on the end of each of my fingers, it kind of do this kind of motion. And I think that will translate directly into inertial drive without translating to any other direction. And that is it. So our lab is here in Hawthorne, New Jersey. If anyone wants to come by, reach out on our website, and we'll set you up with a with a tour of the lab.
Awesome, Mark. That is super cool. Okay, so technically this is a lab update, but you know what? I still want to bring the folks in. Let me see. I'll bring everybody in. Put your hands together for Mark Sokol. A rushed presentation. We're 5 minutes over, so Mark, we need to run now.
Excellent.
So,
Yeah, I have questions, Mark. So maybe.
Oh,
next
go
time.
ahead. Go ahead. Yeah.
So your explanation there in the beginning had me. I just want to kind of understand. So this Alsophan theory is dependent on. You mentioned basically that the matter was like light spinning in on itself. So does the Alsophan theory depend on light being solitonic?
No, Alsophan theory. First of all, you should understand something. Todd DeCiato, who's here in the chat, has his own theory as to why the experiment would work. Jack Sarfati has his own theory. David Chester has his own theory. Mark Sokol, I have my own theory. And Frederick Alsophan has his own theory. It's an experiment that involves orienting the spin of nuclei, subatomic particles in the nucleus.
Okay, so
why that would create interesting effects is a question that has many answers.
Okay, so but the original hypothesis by Alsophan, did he give a reason why he thought, okay, lining up the spin orientation of nuclei will affect inertia or gravity?
Yeah. So his explanation was the second one that I gave. Basically, he stated that because gravity is doing work on it to disorient the spins, therefore maintaining the spins would be anti-gravity. So it should lose weight and it should lose inertia because of the equivalence principle between gravitational mass and inertial mass.
So in relational physics, there's some well-known or not well-known derivations of inertia. One of them being the Reisner hypothesis, and there's the Siyama and Cook, where Cook used the expectation value of quantum to to figure out the extra 1/3 that was in there that Siyama had. And what all of them have in common is they all hypothesize a zitter, like a motion, internal motion. But what they do is they say that motion is happening in all directions. There's no preferred direction, right?
Right.
So
You're
if you look at
that's
Cook's
part of our paper. The zitter is part of our paper. We're orienting the zitter.
Okay. So if you look at Cook's paper, what he's doing for the correction is he's taking that basically the expectation value of the velocity squared, which the velocity would be the speed of light if it's light spinning in momentum space, like you said, or you said spinning in on itself, but let's call that a phase space or momentum space. So, and there's no preferred direction, right? Just generally. And so there's some kind of
I think that the way they spin on themselves determines what particle it is. It's kind of like string theory.
Well, we'll get back to that. That's a detail, if that's okay. But just in terms of the inertia, right? So the inertia itself in those things, you have, let's say if there is a preferred direction, right? You might get a fraction of the inertia, right? That's if you look at just the Siyama work and the Cook's work, and Reisner's work. So there's already an established kind of physics train in relational physics that can support that. But you have to be saying that, and by the way, those theories also can predict, like, okay, what the force of gravity is locally as well, right? Because inertia is found to be the force of gravity from all the rest of the universe. That's what your inertia is, right? So in terms of that, the gravitational potential is one of the things I wanted to say that's important, is that not many people realize this, but the gravitational potential is on the order of the speed of light, right? So
I just see inertia as spin wobbles of subatomic particles.
Yeah. No, I understand.
But there's a lot of different theoretical frameworks to look at the same experiment and come up with reasons why it would work.
Yeah, I understand that too.
So
Yeah,
I'm not going to sit here arguing which one is correct, because
Right.
I don't even know getting 100% weight loss will determine that.
No, I'm just trying to understand, like, where Alsafan got the idea in the first place, right?
Alsafan got the idea from a book falling off the shelf in front of him.
Okay.
And
So he just
in
said, "Hey,
combination with he saw flying saucer, he figured out that he's got to go to this technical library and figure out what these RF pulses were, and a book fell off the shelf in front of him. That's where this came from.
Okay.
And then he filed for a patent and published a paper. The patent was denied on national security grounds. That's how we have this.
Yeah.
If I could add, if I could add,
is the magnetic moment itself. You can derive that from solitonic matter. So if you look at one of the scaffolding I used in my theory was a quasicle group, right? The Williamson van der Mark theory, and they actually, when you have solitonic matter, like a torus for an electron, or in my case, it's a scroll ring for a proton, because light is spinning.
I do have to go. Jared, you were going to say something?
I just wanted to add, so the one RF UFO instance that we had from 1957 with that 3 gigahertz, we've been using just that one for the longest time. But recently we came across a second one that was 4 years earlier than that had pretty similar RF characteristics as well. So the RF characteristics for the 1957 one was 2.995 to 3, let's just call it 3 gigahertz, with a pulse rep of 600 hertz and a pulse width of about 1 to 2 microseconds. I think it was 1.5 microseconds. Okay, that's the one we know. So this other one we came across from 1953 over in the Sea of Japan was 2.775 gigahertz, 500 hertz pulse rep, and 1 to 2 microsecond pulse width. Very, very interesting that we have, pretty similar ballparks there for our numbers between these very disparate UFO sightings. The 57 one was all over the southeast of the U.S. It was like a 3-hour recording session. And the other one, I believe it was like 20 minutes maybe over in the Sea of Japan. But the fact that we now have a second data point for this RF is quite interesting in how it may apply to what's going on with the DMP stuff.
And people who get burns from getting close to flying saucers, they look exactly like microwave burns. The crop circles look exactly like microwave effects on the crops. I mean, everything's pointing towards microwaves. And then tinfoil hats. I gotta go, guys. Peace.
Okay.
Mark, thank you, man. Thank you. Okay, so yeah, guys, anybody else have lab updates? Curtis, do you have lab updates? Or Drew, do you have lab updates? Drew,
Yes.
Drew, take it away, sir.
Okay. Yeah.
You want your screen share?
Tim, can I put a picture on the screen?
Yeah. It's the plus button. Hit the plus button.
Okay.
And then share screen, and it should let you pick a tab or share the entire thing. There we go.
Okay. Pretty much all my efforts for the last couple of weeks have been focused on, and I won't use the exact wording, but this blanking thing. It turns out that when you try to explain something really complex like push button, watch spaceship go up to people with money, they don't get it. So you have to do it so simple that they do get it. So this is about as simple as I can make electrostatic or asymmetrical electrostatic pressure thrusting example. Scale, box, and what you don't see is a handheld like a phone with a button that says on. And the theory is, I'm going to turn it on, going to zero the scale, press the button, and the gray box of closed magic is going to lift upwards at about 1 gram. And hopefully there'll be oohs and ahs and woos. And then I'm going to press a different button, and it's going to go back to 0. And then I'm going to press another button, and it's going to go -1 gram. So, whatever, or +1 gram. So it's going to go -1 gram upwards, +1 gram downwards. It's been eating my life. So, just thought I'd show it to you. Open air testing.
Yeah,
It is
that's
a nightmare.
That is super exciting, Drew. That is super
It is a
exciting.
complete nightmare. Because in vacuum, I can run, 10 to the 8th field strength without arcing and sparking and plasma death and melting of test hardware. In open air, I can't even hit 10 to the 7th, maybe. Mid 10 to the 7th, if I'm lucky, before something gives way and it arcs and sparks and get to throw away a couple $100 worth of materials. So anyhow, that's it. Any questions?
Oh, thank you so much.
Okay.
Thank you so much. Okay, well, yeah. So I think that maybe
I have one question for Drew.
Go for it, Jared.
So how much did the numbers change on the scale for the box on there when you turn it on? How much shiny ooh-ah did you get out of that one?
This isn't working yet. All the pieces of the puzzle are working. But the actual power supply that can be punched on with a phone, that shows up tomorrow. And I'm actually going to get graced with Dr. Bueller's presence. I don't know exactly what he's showing up for, and I have no use for him at the moment. But he is showing up at the same time as the new power supply is showing up. So we'll see what happens tomorrow. But tomorrow, as at the very most that's going to happen is 1/10 of a gram. We can pretty much make 1 millinewton on command now. And the goal is going to be to just put 10 of them together and hit the button and make 10 millinewtons, which is 1 gram. So, again, it's nothing compared to what we were doing in vacuum 4 months ago. We were hitting 50, 48, 50 millinewtons. But of course, it took 200,000 seconds to get there. But still, we were doing it. This is a very, very much less wow factor. But we showed an early predecessor of this to some people a couple of years ago, and it happened to be the guy who invented the CMOS chip. He used to be the president of Apple, or he was the CEO of Apple, and he was a CEO of Siemens or something. He was like seriously into this part of the universe, and we were showing him 100 micronewtons, and he went crazy. He's like, "Oh my God, that's just amazing," Now we're at 1,000 micronewtons regularly, and this test is going to be, whatever that is, 10,000 micronewtons, or 1 gram of displayable thrust.
So, Tim, if I might, I don't have a lab update, but a little theoretical update. So the Heim theory website got some major expansion over the last weeks. And we also have a specific site on Heim's experimental work in the 50s and 60s with the Contra-Barry effect, which is like, it is based on a microwave system, right? So it ties right into the discussion, which was just there. And I maybe want to emphasize again something that Michelle said. So that theory and experiment have to come together. And I do think that especially in the stuff that Curtis is doing right now in the UQFT, a lot of the ideas that Burkhard Heim was working on are realized once again as in a theoretical framework. And we're moving into a direction which is very, very interesting. So Burkhard Heim talked about built-in properties of matter, and you find this the same in UQFT. And I would say probably the following sentence is correct. If propulsion without propellant is ever going to become physically real, and I think it is in what Drew is doing and what the Mega Drive is doing, it won't come from internal forces moving in a closed system. It will have to come from a real coupling to a deeper inertial gravity structure of some kind, right? So the key question here is, what is actually the reaction partner of the propellant propulsion system? And in Heim's theory and in Curtis UQFT, we actually have a potential answer to this kind of question. And so this is what's really exciting to me, that we probe this kind of answer deeper. And we have to get to a point where we can get actual computations out of the theories, which then are matched to the experiments that we're doing here. And I think all the experiments that are shown are very, very important, because they all, to me, they show one underlying thing. And this needs to be explained by this coupling. And we need to explain what is actually the reaction partner in propellantless propulsion.
I have that explained in my thing. The only thing I'm missing is, or guessing, is the vacuum energy density. That's all. But if I had known that, then the math that I have aligns with experiments. But that's the only thing that I'm missing.
Okay. Well, guys, let's go to open discussion, if that's cool. So it's about 5 p.m. And if you want, I can start.
Sure. Tim, can I share my screen a minute?
You can. Are you doing an update, Curtis, or are you just open discussion?
Yeah, I'm going to follow up with what I was talking to Mark about.
Yeah, because I have a couple of things I wanted to show quickly as well. But I would say take it away, Curtis.
Okay.
There we go. Okay,
so I want to continue that discussion about what the magnetic moment is in a solitonic matter model. Okay, so like I said, for UQFT, one of the theories I used was the quasicle theory, Williamson and Vandermark's model for matter. Specifically, they worked on the electron, right? And they had some preliminary models for proton and neutron, which somebody named somebody else. I'll show his work later. Vivian Robinson. He expanded it to that. But the thing about the electron is, basically you can form electrons and positrons or leptons by taking gamma rays of the right energy. They come together. They have to be polarized the right way, so they have to have a circular polarization. Otherwise, it doesn't happen. But then you get this this kind of nonlinear effect where they go off and they spin in like sort of a momentum space. So a good picture here is down here. So this is a good way of visualizing it. So you'll have this electromagnetic radiation like an E&M field, right? E cross B. And as it moves along, it's, instead of going straight, it's going kind of in a circle in the momentum space. So it's sort of vibrating. And in that momentum space, it has to go 2 times around, okay, for it to for its orientation to be the same. Now, its orientation, the way you get an electron, the way you get charge, is the electric field is either pointing outward or inward in that electromagnetic radiation as it propagates, right? So then you have, okay, well, what about the spin? What is spin, right? Spin is actually has to do with magnetism. It's a magnetic moment of the particle. So for an electron, where you have light spinning in momentum space and the electric field either pointing outward or inward and looking like a point, you get a magnetic moment, right? A small magnetic moment. And why does that happen? Because the magnetic field is twisting around. And so it averages to a certain direction, either upwards or downwards, right? Either spin up or spin down. And this model is well worked out. And, you can go into their site, read about it. There's papers. And what I want to say is that for UQFT, if you take the low gravity limit, you can recover basically the mathematics for this theory. It's correspondent to this theory. The fundamental mathematics are a little bit different in terms of like the group I'm using and the group they're using. But again, it can map to it. They have biquaternions, which you might call, or vector quaternions or quaternions in it. And my theory is UQFT is built on the quaternions that Mendel-Sachs used, right? So yeah, it's really good information, and I would like anyone interested in this stuff, I would look at that. Now, the second thing is important to keep in mind is what inertia is, right? How do you get inertia from something like this? How does this experience inertia? And that's in my talk, right? Now, the thing about it is that I agree that like you can explain magnetic moments and explain, so-called anti-gravity with other things, but you're not really explaining what inertia is. That's something that's missed. It's kind of moves into, and people talk about it, and they kind of go back and forth. But what is the specific mechanism? It's not nailed down, right? So in the whole relational work that people have been doing, like Siama, like Jim Woodward, they've been trying to nail down, okay, what is inertia, and like what can I use it for, right? So that in Jim's case, he was figuring out, okay, I understand inertia to a certain extent. I can actually do something useful with it, or actually potentially useful, and show that it's actually an effect that we can show that it's coupling to the rest of the universe in a more direct way, right? Because if you can get inertial effects, then there's absolutely no question. But again, there's already experiments that show that inertia is coupled to the rest of the universe. We already know that. Those experiments are well documented. Newton's bucket, for example, or the Bach bucket, right? There's lots of fundamental things. So that's not a question. And the thing to keep in mind, again, is the big surprise, if you start thinking about these lines, is that the gravitational potential of the universe is at the order of the speed of light. And so when you put all this together, it sort of now makes sense. If matter is solitonic, and the gravitational potential is the speed of light, and gravity affects light, it's all the same thing, right? So fundamentally, they're very, very coupled. Okay, so that's kind of the reveal, right, that we've gone through for inertia. So that's what I wanted to share.
Curtis, thank you, man. Thank you. Here, I will do a super quick share also. I got a couple of, let me see. I'll just do a share screen, and what I have. Okay, so I'm going to start thing. I'll just kind of run through what we got. So this is Panic. This is the NMR conference, Materials and NMR Insights Conference for 2026. Mark Sokol is going to be attending this. Depending on time and travel and all those other exciting constraints, I might be able to attend also. And if I do, I'll at least get photos of Mark, hopefully. So we will see. So that's the Panic conference. It's panicnmr.com. I'm probably not going to recommend this to the audience because NMR stuff, this is really, really technical, and most of it is not related to propulsion. So you know, a lot of what they do with this is like drug discovery and you know, batch verification, stuff like that. So it's you know, not normally related. Although, as Mark said, they are getting excited about his work. This is McMenamin's Hotel Oregon UFO Fest. This is the one that is down near Jared Yates. I am going to take the bus down there. It's going to be exciting. Let me see, who do we have? Jason Martell, Matthew Sadaugas, Rebecca Charbonneau, Jeremy Corbell, George Knapp.
You still have the Panic stuff up.
Oh, did I? Oh, I'm sorry. Hold on.
It didn't
Share
switch.
this tab instead. There we go. Okay. McMenamin's UFO Fest with Martell, Sadaugas, Charbonneau, Corbell, George Knapp, Kelly Chase, and a secret guest. I have no idea who that is. So my hope is to take the bus down to Portland, spend a little bit of time getting some video and photos of Jared's new lab. I want to try and get updates on Isaiah's SEG. And so I'm super excited about that. Then I'm going to share this also. I'll share this tab with you. This, I just hit publish on this. This is kind of sort of a book review talking about gravity control of present technology. And this is David Alzafon's story of his father, right? His father's work, which is, again, kind of Mark's, that is Mark's inspiration, among other things. You know, as I've been saying, Mark is positioned for this better than anybody else. He is working with David. He's working with the estate and the son of the inventor of this. Mark knows Richard Eskridge. Eskridge has done related stuff. Mark knows many DNP and NMR experts. He's been to conferences. He's doing the homework, and he is building the equipment. So in terms of NMR and dynamic polarization, Mark is there, and this is part of the legacy of that. So basically, we're trying to kind of honor that and help explain that and help promote it as well, right? So that is that one. And then let me see. I'm gonna have to let me bring up Flickr again. Okay, maybe 2 seconds. Okay, and I will share this tab. So this is my Flickr profile, which is kind of my clearinghouse for photos. So I was just at Falcon Space. Yeah, there we go. So I shot these. This is a close-up of Mark's meteorite. You can see it has very pretty melt texturing on it from when it was falling to the air at high speed. Then this was Al Bauer's device. I have video of this that I will post as well. I got to see this in real life. This is the one with the little thing that floats in between the two grids. It's ion wind. There's no magic to it at all. But in a weird way, it is kind of magical because without any wires connecting it, it floats in that ion stream that will dance around in a circle. So I got this. This is Mark's Connects. This is the force field experiment. Charlie Bueller visited, and so he gave Mark lots of feedback on it. And then I got a couple cameo pictures. There's Tom and Mark and Pinky the dog. So we'll see. One of my projects is I'm working on Mark's website, and we may use those for that. Also, Deep Tech Week. This one I was very excited about. If you guys follow me on Twitter, I've been posting this on my Twitter account. It's Eric Weinstein. Eric was talking about the limitations of the scientific establishment, more or less. Then let me see. Manelli Max Derek Shawnee. I'm trying to find a good photo of him. He was talking about foundations of physics. He's with the John Bell Institute. Then our very own beloved Dr. Charles Bueller. We were right near Mark's. That was why he visited both. He was talking about the work that Drew was doing because he is Drew's partner in crime, so to speak. So he was talking about the work that they're doing. I did get a couple of nice keeper photos of Charlie there. Then, not surprisingly, Mr. Sokol himself, Mark was speaking on DNP, the presentation that he just delivered at APEC. He also delivered that live on stage. And then Mr. Harold Sonny White, and I have not seen him in over 20 years. It was wonderful to finally see him in person again. I used to see him at the STAVE conference. He was talking about the Casimir Effect work. Again, absolutely breakthrough. The last thing I thought I would see in my lifetime is real zero-point energy. I swear to God, that's what it looks like is happening here. So I believe this is all of them. I don't think they left anybody out. They didn't switch the slides. They left Sonny's up for a while. And that's the panel slide. So not all of these were amazing photos. It was a dark room, so I had to use a special lens to let light in, but then that created shallow depth of field. That is why Mark is blurry. So I think that's what I got there. And those are all up. You know, you can just do a search for Tim Ventura, Flickr, or whatever. Again, those photos, I put those up. Those are kind of public domain. The only thing I would ask is if anybody wants to use those, don't make the people in them look bad. Don't use them for negative purposes. Don't use them in a critical way, right? Like the reason that I take those photos is to help promote and inspire and share vision. And I would hope that anybody who decides to use them for blogs or whatever would do the same. So
I think we all need to put our hands together for Tim. Give him a big hooray. He needs it. Thank you.
No, you don't need to. I don't need. You know what? I'm happy just to try and move the ball forward. I mean, you guys are the ones doing the work. I just follow you around with a camera. You know?
That's the hard part.
I disagree with that, what you just said, Tim.
A camera and a growing collection of lenses. That's the other. It's getting bigger and bigger. And bigger. So yeah, and in fact, I was talking to David Chester. Now that Thorsten, I did not realize that you were working with the neutrino voltaic group. I'm really excited about their work, and you're working on consciousness, and you're working on Casimir Effect. So I was chatting with David Chester, and I was like, let's go to Germany. Let's go to Germany.
I got to tell you, Charlie and David seem to have struck up a physics friendship of some sort, because they're texting each other at all hours of the night, and I'm sure it has something to do with the time differential between them. But I see some very curious text flying across that there are no English words in these texts. It's all theory and babble, and so far I've gotten nothing out of this, but you know, I'm sure something wonderful will pop out of it.
That's collaborative. That's cross collaboration. That's
Yes,
what, like Curtis and Michelle and Paul March and Jim when he was with us. I mean, they had a really tight knit group, and they were doing emails like that, and you know, different working groups, right? I'm sure he's working on Heim theory, and you know, Jared is working on a few different things. And with all of these different little working groups, you get these emails and signal chats now, and it's wonderful, right? That's because I mean, I've found this at least. Like if I'm working on something, you hit a roadblock, and sometimes you just need a different perspective, a different paradigm. You know?
Yeah, and Tim, like you're a very big part that we actually can connect, right? You're making this conferences and giving us the place to connect and to get to know each other. That's a very, very important part of the work. Giving us a platform, giving us a point to meet, to connect, and to form this kind of groups. So yeah, the applause is definitely deserved. And I totally agree. Like I have some very amazing talks going on with a lot of people from APEC, and it's just getting more. And I hope Thorsten is going to be one of the persons that's going to be involved more in the future. with me and my work. And yeah, if you come to Germany, I'm definitely would like I would come to Berlin as well to that, or you can come by Hanover anytime.
Yeah,
You're really welcome here.
I
Also, I have a very
flew
interesting conversation with David
Germany.
Chester. Yeah, would be nice to visit him in person.
Then the other thing that's, and again, this goes back to the Casimir Effect stuff, but I was talking to Michael Perrone, and he gave me some leads to follow up. Folks who are familiar with his work, he is a big fan of what Dr. Daniel Sheehan is doing. Sheehan and Vladislav Kapek, they wrote a book that he was talking about. He also, the OnLab, right, had some stuff. Then he also talked about Germano di Abrahamo. Had a self-charging thermionic capacitor, in theory, but not experiment. Then Jovian Systems and Bernard Hayes claimed vacuum energy with hydrogen or helium through Casimir capillaries. Then he was also talking about Paul Thibodeau. Paul Thibodeau is doing something very similar to what the Neutrino Energy Group is doing. He describes it, discusses it a little bit differently, but you know, he's basically trying to harvest energy, harvest ZPE or rectify thermal energy using graphene. And there's Garrett Modell, Sonny White, and he listed a few others as well. So one of my hopes, well, I'm crossing my fingers, but what I'm going to try and do is download a bunch of these, dump them into AI, and see if it can find some similarities. So, and it was, Michael already had some. He had said, he was talking about capillary systems, which I thought were interesting. And then he had talked about basically biasing a diode to potentially harness ZPE. So there's a lot there. And then Thorsten, one of the things that I found from Thorsten, and he has since gone beyond that, was Thorsten, you had a tuning fork, micro tuning fork based Casimir Effect sensor. And then when I asked you about it, you said that's you've improved that. You have another version that's already beyond that, right?
Well, there are reasons why I'm using other setups now. I think I wrote you an email. One thing is it's not so easy to track resonance frequency. It's not as easy as tracking a voltage or the point of a laser. To actually track the resonance frequency, you have to kind of wobble the frequency a little bit to actually be sure you're on the resonance. And this is one reason, but the good thing about the tuning fork is they have a high K, so they're very stiff. If you're running the Casimir the way I'm doing it now, the cantilever has a very low K and is very soft. Otherwise, you can't measure the force. So the tuning fork has charm. It's cheap. I mean, it used to be cheap. I have a bunch of them lying around. You know, you used to get them for less than $1. So it's always fun to use something which is mass produced. I think they make about 1 billion of them a year for watches, you know, so it's super mass produced, and yeah, it's a good starting point.
And so Bill Alec, many years ago, Bill Alec did a different experiment. He was attempting to compare two of these, and I know that Jared has experimented with that as well. And that has its own set of issues because you have to synchronize them. But for folks who aren't familiar with this, what I learned was these are MEMS devices. They're tiny, tiny tuning forks. So people, they may think big, but you need to think like microscopic sized, and they vibrate at a specific frequency, right? And then if you change the energy or the mass, it's going to change the frequency of that mechanical vibration.
And if you do it in vacuum, they have a super high or very sharp resonance.
Yeah, yeah.
It's much sharper than in air.
That's really exciting. So I am a judge. This is just my own like focus, but like we're reaching the point with a lot of these experiments where we need more tools to analyze them. You know, I mean, we need better tools and more tools, and then there are times that I've wondered. If this would apply to any of these experiments. You put it in the chamber, you're running a test, and it's like, okay, here's what we're looking at, you know, voltage on a scope, or we're looking at like camera feedback, right, depending on who's using what. But like, what if we had like your device? What if there's something else happening that we're just missing? You know, like we're just not seeing it because we don't know to look for it.
No, you're absolutely right. You see, one of the things I learned in the consciousness research, which is also quite difficult, once we had like a jam session where we brought all our equipment, and Dr. Falcon, he also, we visited him, you know, which is super scale, you know. I don't know if you're familiar with his work, you are. So we had this session, and we ran all the four different instruments at the same time, you know, and it was fantastic to see that if we were, then we had like healers come in and other people, you know, and the best thing was we had one device which is using random numbers, you know, and his engineer came who is usually, he's just a technician who works with his scale, you know, which is like a $500,000 scale, right? So he really loved our instruments because it had a display, so you could immediately see the result. And on the scale, you need to analyze and download data, you know. So he asked, how did you do this? You know, okay, what operating system is it running? And he had so much love for this instrument. He had enormous influence on that random number generator, you know, because it was, while the healer who was very good with the scale, he said, oh, I don't like that instrument, and the instrument doesn't like me, and he had no influence at all on that instrument.
Oops. Okay.
So yes, it's great to run totally different sensors and instruments, you know. You're surprised to see some subtle influence. Okay. I think I'm going to go now. It's a bit late here.
Yeah, it is late. Thorsten, thank you again. Thank you. And I emailed you, actually. I emailed you a few minutes ago. But yeah, let's definitely connect. We'll stay connected. I want to learn more about the consciousness, and I'll share. I shared a couple of things that I'm working on there as well. So.
Okay. Thank you very much for this great
Thank you.
event.
So it was truly a pleasure and an honor to have you with us today.
Bye.
Okay, well, guys, yeah, so open discussion. Jared is being suspiciously quiet today. Maybe Jared is tired.
I am querying ChatGPT to try to understand the Drew thruster. It will forever in my book be called the Drew thruster.
Okay, well, without describing anything that we've been talking about, what is this new idea you have for getting non-garbage out of ChatGPT?
Yeah, I was talking to another APEC guy, and he came up with his own AI. He generated his own AI from scratch and was showing it to me the other day. And his name is Ito. Anyways, he was showing this to me, and I was blown away. The gist is that it starts at like foundational logic, right? And foundational logic is pretty much pure math, right? And so from that, you can build knowledge bases, which are called an ontology, right? So an ontology is like a group of these truths describing a certain category, a certain thing, right? So you have the ontology of like electrostatics. You have the ontology of the Geneva Conventions, or, you know, fair, what's considered fair killing, right? Or you have the ontologies of the animal kingdom, right? Or the family tree of life, right? that would be considered an ontology. So what it is it's like you have these modules, these ontologies, and so you can selectively like put those in, and then you can basically turn on or off certain ontologies, which is kind of like turning on or off certain neurons in your AI. So if it's hallucinating or if it's giving you answers through or crap, it's because it's drawing from the wrong ontology to answer the question. And it tells you which ontologies it's using to answer your question, so you can go in and you can deselect these things. He actually asked me to share this with as many people as I can, because right now he's built it out so that it has about 4,000 ontologies or so. And that's drawing upon a few hundred white papers. So he's trying to ground it in his truth as much as possible. He's actually, I think he might reach out to Tim and see if he can't get the thing polished up enough that it would be a good APEC presentation, because as far as tools go, this thing is insane. His queries, he was showing me, it all operates in browser, and his query took like 150 milliseconds to answer the questions. Like insanely fast and insanely small package, like 4 megabytes in browser, like insanely efficient, insanely fast, and the potential is mind-boggling for how you could end up taking this. But I don't want to steal too much of his thunder, because I think that he would present it far better than I ever could present his ideas. But the one thing that I will do is I will share the GitHub repo for that, so that if other folks want to look into it and read about it more, they can. So if
yeah, Jared, that would be very interesting, because we're working in the
Yes.
Heim theory work group also on a specialized AI system, and one of the key features should be the symptometry of Heim, because it's basically you can use it to translate different frameworks into each other, and to also sort different frameworks onto how good they can answer a certain question. And so it's a very so the idea goes in the same direction, that you use different you call it ontologies, it's fine, to answer different questions, and you prioritize certain over others for certain questions. And yeah, so yeah, maybe also if you want, you could connect me to the guy. Maybe he's interested in throwing the symptometry into the mix of the ontologies he's using.
Mm-hmm. So right now he's gotten about as far as he's going to get for creating his own ontologies. And that's why he's trying to share the GitHub publicly, which if Tim could allow me to share screen. So here's the GitHub that he has. You can see his username and the name of the project. But I'm just going to put this one, blast this one out there, because he really needs other people to use this thing and create more ontologies for it, right? And creating an ontology is kind of a process, because you have to base the whole thing in like logic math, and you want to be able to have like white papers associated to that, right? The whole thing boils down to just taking category theory, like taking all AI, stripping away all the statistical based AI, going back to the fundamentals of what AI should be, and saying, no, rather than doing statistics of these neurons, do ground based truths of, A equals A, right? We know that this thing is this thing, or if A equals B and B equals C, then A equals C, right? That starting from a logical standpoint is a great way to ensure that you're not going to have a hallucinating AI.
Are you aware of the?
That's the only thing it's doing. It's only doing math.
But does it do it right?
Yeah.
When you tell it to multiply 2 orders of powers of 10, does it get the right answer?
Yep.
Okay, well, that's a huge improvement, because the chat GPT I worked with a couple of months ago, it couldn't do math.
It's taking your query, converting it to binary, doing the math, and then spitting it back out. And as for like text output, the dictionary is one ontology, and the proper like underlying structure of grammar and stuff is a ontology. So he's able to make this thing like be able to speak for like translating between languages. Like the way ideas are conveyed in different languages, yeah, it's different when you use different words, and yeah, there's some subtleties in those, but there's like an underlying substrate there that is language that you can use as the lower level thing that this thing can then spit out the ideas in the different languages.
Okay.
Yeah, so maybe he should also get in touch with the Laws of Form group. I'm not sure if you're aware of them. So Laws of Form is it's actually, I think it's a book by Spencer Brown, and there is a whole community around this work, because it's like the book basically starts by it is foundations of logic, what they are doing. And yeah, this sounds very interesting for them, and vice versa. That's also, it's a very, very active group with dozens, if not hundreds of people working on the foundations of logic. I'm quite sure that at least one of those people would be interested in feeding that system.
Nice. Yeah, Joel, I will see if I can't get you in contact with Ito, because I think you might know some folks. And Tim, if you know any AI folks, if anybody knows any AI folks that or computer programmer type folks that would be interested in this kind of idea, because I think he's really got something here. This one's big.
Okay. I mean, I think you met them last year at the UAP Hackathon. That was probably the biggest collection of programmers that I've seen in quite a while, you know. And then for AI, I think we're all using it now. I mean, I'm using GPT and Midjourney for graphics. And everybody else is using Claude, and they yell at me for using GPT still, but I think it writes better.
Yeah, it's less hallucinating, but that's also like so one he's also loosely connected to APEC and to Daniel Davis, and he's a physicist as well. He has shown mathematically that basically the more you restrict the hallucination, the less creative the AI gets, and also it restricts to basically it becomes an orthodox within the established field of knowledge. So if you want to try to do new ideas, a less hallucinating model is way less compliant with that kind of ideas.
So,
and it will start to argue, no, that can't be. So GPT through the last versions got way less hallucinating, which is a good thing in one way, but on the other hand, if something is not established, it might dismiss it or try to formulate it very vaguely and so on.
So what I have been doing is using transcripts and sometimes deep research, as well as scientific papers and things like that, to try and anchor it. But it's different for me, because like what I'm trying to do is take existing thoughts and communicate them, you know, and like one big part of it for me is can I take something that's written as a white paper and get it to translate that for a more general audience? Because not everyone has the wherewithal to read scientific papers all the time, you know, and even if they do, different people read, different people communicate in different ways. So the anchoring part for me is pretty big, but then in another way, I'm not as creative as you guys are. I'm not asking it to derive new things. So I don't know, so, you know, it's, what do they call it? 6 this, half a dozen of the other. That's been one of my, pretty much everybody I know, like all of you guys are doing actual science and engineering, and it would be really nice if AI was better at that.
That would be nice, but otherwise, what should we do then?
Well, I
mean, actually, all I use AI for is mainly if I
take my instrumentation, whether it's, through the video, through tracker, or if I'm using picoscope data or whatever, that data gives me CSV files. And in the CSV files, it gives me, when I'm using tracker, it'll give me acceleration, it'll give me velocity, it'll give me time base, and also will also calculate out momentum. And I'm taking that stream of data and I'll import it into AI and tell it that here's my velocity, here's my acceleration, here's my momentum, total momentum. Give me a graph. And it's producing a graph. And I will also cross-correlate. Let's say if I use ChatGPT, I'll cross-correlate it between Claude, make sure that I get this same processing of the data. And I'll also cross-correlate through X. And there's another one that I use. But there's like 4 different AIs that I use to cross-correlate the data to make sure that whatever I get is agreeable. If it's not, then I go back and take a look at the data myself. But it's a lot faster than me doing spreadsheets. So to me, it's a tool, and it's gotten a lot better in the last 2 years, exponentially better. And I've seen what some of the work it's done for you, Tim, as far as taking all this data on these papers and stuff and assimilating it down. And it's done a very nice job. Sometimes I think it tends to ramble on an awful lot.
Some of that is me. I try and write longer stories, and part of that is because I'm trying to do long tail Google search relevance. Google wants longer stories. So it's like, write me a long form article on X, Y, or Z. And I don't know. Part of that is just because we're a niche community, and so it's a challenge to break through a lot of the mainstream news sources. But, and then the other thing that I lament, is unfortunately, and this is just people go for name recognition over substance. And I found that because I see the search results, I see the search traffic and all of that, right? And the biggest, in terms of pages on the Alt Propulsion website, the biggest ones, the page on Charlie Bueller is giant, and that's awesome because he's with us, he's doing valid work, he's here right now, he's working with Drew, right? That one I'm happy about. But then another page that is massive on traffic is the story that I did on Mark McCandlish. And that's valid. It's good historical info. There's nothing wrong with it, right? But he passed. Other people have picked up that torch. It's kind of things have moved along, and it's I wish that people would be looking up things that were more current and relevant today. But they tend to go by name recognition, and that's just a side effect of the internet. And you see that on YouTube also, right? That's why Joe Rogan gets so many views, and and other authors, they drill down 5 times more, but they're obscure. So.
Well, it is a tough nut to crack, saying how do I get more views? And you don't want to end up being sensationalist. You want to put out the truth. So it's a good call there, Tim, to make a good decision on what you promote.
And then for me, and I'm not sure how other people use AI tools, but I haven't had a problem with GPT complaining about physics too much. A lot of times, and on the rare occasion that it does, I'll say to it, okay, please list where this differs from mainstream physics. But I've met a lot of people who are it hates my physics. It says this is wrong and that's wrong or whatever. like I typically, I haven't seen that with what I'm working with, but like it will say, okay, this is not supported by mainstream physics, right? And stuff like that is probably still touch and go, I guess.
Yeah, I try not to let it do formulas. I try to use it to see patterns. One of the patterns that I was very susceptible of, or suspect of, was like in Woodward device, is the fourth order harmonic. Nobody really, and the whole group, I mean, all the way from Dr. Jose Riddell and so on and so forth, nobody really grabbed onto the fourth harmonic. And I did some research and so on and so forth. And I was very suspect that it is a key to making the device do what it's supposed to do. So I used ChatGPT and also Claude and said, here's data that I have. Let's do analysis of that data and that data set. What do you determine from that data set? And both of them came back and said, a key here is the fourth order harmonic. Because of the fourth order harmonic and how it relates to the phase of the drive working, the drive actually doing thrust. It's critical where you get the phase change that you get the thrust, intense thrust impulse out of it. And both of them came up with it. And you know what? I agree with that. I suspected that to begin with. That was kind of reassuring to see that feedback. And I found that very useful. And I thought it was a good breakthrough. So that's, yeah, it's a tool. It's how you use it.
Michelle, I had one question for you from your work. What is the longest sustained thrust that you guys ever saw? Not the amount of thrust, but just longest sustained. Oh, Joe, could you mute? You got loud clacking. The longest sustained, non-zero thrust that you were able to get.
20 seconds.
Dang.
Yeah, I know everybody is used to seeing old GEM displays where you get these spikes of, but the problem was he was doing a high-speed sweep through the resonant frequency, and when it hits, it gives you a big old spike. Jim liked that. I mean that was music to his ears. And I don't know how many Zoom meetings we had. I said, slow it down, Jim, and give it. I don't care if you get an extra amount of force out of it when you're doing a sweep through dp over dt. I don't care. I'm after data. I want clean data, and he resisted that. So if you slow that sweep down and you go through it very slowly, you don't get the increased thrust component out of going fast through it, but you will get thrust, and like for 20 seconds. The one I presented, I think it was just today, it was 11 seconds, and I think that was a good show of force. So for 11 seconds, I showed 175 millinewtons of force.
And it only works though while it's being swept, right?
No.
Oh, so if you manage to dial in on it, that's how you hold it.
Yes. It has a Q, which means it has a particular frequency that everything syncs. Everything works together. The harmonics work together and everything, and that's in a particular envelope of frequency. It's approximately 150 to 100 hertz wide. So if you sweep into it, you'll actually make all the conditions until you sweep out of it. You do not have to sweep into it. One of the things I'm changing, and I'm setting up to do this here, is not sweep through it, but pick the absolute resonant frequency in the center, which means I'm not going to be consuming any more than like 2 watts of power for the device, because I have a high Q in it, and all the energy is going into Q. I can turn around and take, instead of a constant signal into it, I can put it into an AM envelope, so I can pulse it and pulse it and pulse it and pulse it and pulse it. And that way there, I can get a sustained acceleration. And I will be able to hopefully show that on the frictionless device that I got, the air-bearing device, where it just goes up, holds, and sustains until I turn the signal off, and then it'll go down. That's where I'm going. That gives us a 2 watts I can deal with as far as the device. Let's say the device in the enclosed tube. One of the things I do have here is I have a pyrolytic carbon. It's a sheet of pyrolytic carbon. It's a higher thermal conductivity than gold or copper or whatever. And I figured out a way to attach the pyrolytic carbon around the device so that it'll conduct the heat away from the device. Inside the tube, I'll seal it all off, and I'll fill the tube with helium. Not hydrogen, but helium. Helium is one of the best gas thermal conductors there is. And I can cycle a little bit of gas through that so I can pull the heat away from it and keep the device at a very constant temperature at a low wattage consumption. That way there I can have a sealed environment. I'm pumping through helium to pull the heat out of the device. I've stabilized the device thermally, and then I can get a sustained thrust. The goal here is to turn around and take that configuration, and I've set it up so that it's small enough that it'll fit on a CubeSat, 4x4 CubeSat, so that I can set the entire thing in a CubeSat, enclosed, and get constant acceleration. If I get 200, 275 millinewtons out of that, it's a significant acceleration. That's the direction I want to go. So that's the focus I'd like to do. And then on the other hand, I have this other thing that I'm doing that I saw results years ago that I couldn't follow through with because I just ran out of funding. That also reminds me of rotating magnetic fields and collapsing modes within a device, within a cavity, RF cavity. I saw some significant thrust. I actually destroyed my device. I actually broke the end of the device. So anyway, that's my goal, is to take what I'm doing here and port it, the findings, the data findings, saying this is why it does what it does, and port that into controlling this other device. So I think they're both working in tandem. That's where I'm going. And I did some simple calculations on that other device that I literally broke, and it gave me some crazy figures of like 500 newtons. So we'll see. It's fun. I'm sorry, you get me talking and I go crazy.
It's quite exciting work. Drew has set the bar though so high at, what is it, 30 days continuous thrust. Like 20 seconds is dang impressive for the Mega Drive. So that is dang impressive compared to the pulses.
I don't think of this as a competition. I just think this is
it's a completion.
You do?
We're all working together.
518,400 seconds. I got bored and turned the damn thing off because I was running 24 hours a day, and I had to go to work.
Well, congratulations. I've been doing this I started in 2015. I did it for a couple of years, evaluating the M drive, which I found out that was, and I published it was total bunk, spam in a can, and then I joined the Woodward.
In case you're wondering,
Pardon?
we know how to fix it. We could actually make it make thrust.
Yes. Yeah, I used a modified version of the M drive. Matter of fact, I would change, I would publish on NSF, because there was a big blog group there at one time. I published a change that I would do on my drive on NSF, and 2 months later, I would see Scheuer do a same change on his. So I thought that was pretty funny. But yeah, I think it has potential.
No, it doesn't.
I think it has great potential.
No.
But like for you and for I, you've worked with Bueller's stuff, and I've
Bueller
been
has
working with
worked
Woodward
with my
stuff.
stuff. We need to set this record straight. I am so tired of being told that I'm on his team. I'm going to fire his ass. That's it. Monday. I'm going to get me a new physicist. Continue. I'm sorry. Hey, are we going off of a record anytime soon?
That is a Tim question.
Timmy's not on the panel.
And Drew, yeah, maybe I don't think you should get a new physicist, but maybe you should expand the board of advisors.
Okay.
And maybe not only to Bob Lazar, but maybe also Curtis Horn, because I think it would be very, very interesting to see his theory really applied, not just to the Mega Drive, but also to your and other experimental setups. And that will take some time, right? Because he's at the moment working alone on that kind of front. But that's what we need. We need a theory that can explain the experiments, and the best would be if the theory can not just explain one of the experiments, but multiple of them. Because yeah, a theory and one experiment is strong, but a theory and multiple experiments is so much stronger. Because one of the critiques also of the experiments is, well, this group of people is doing the experiment for a really long time, but it's not verified by another very sophisticated group of people, right? And that's not your fault. You're telling people to replicate your work for years, and nobody is doing it with the amount of rigor and that it would need, right? But if you have the Mega Drive and your kind of system and one theoretical explanation for it, that would be extremely strong.
Sure. I don't know. A lot of networking popped out of this, whatever that thing was I went to New York for. Tech Days, Megatech, whatever it was. But in that loop, apparently, Dr. Bueller got to have a one-on-one for quite a bit of time with Bob Lazar, which that's kind of cool. I really didn't know who he was until a couple of months ago when I watched the Joe Rogan. There was an old Joe Rogan version of it, and then I just found out the guy's worked on UFOs, so that's really cool. So in theory, he's supposedly going to try and figure out some way to hook up and check out our work.
Yeah, I think that's an interesting angle, but as far as I know, he doesn't have a full theory set out
No, he
that he can apply.
He's supposed to be an engineer.
Curtis has, so he should apply his theory not just to the Mega Drive, but also to your work.
Yeah, I got nothing against physicists. I think you're one, but they're useless, as far as I can tell. Yeah,
I kind of agree. If it comes to you haven't seen physicists being useful for quite some time, right? But that is because we didn't have any any real success in changing the fundamentals of physics for quite some time. The moment that we actually do that, and I think with Curtis, we are currently doing that, you're going to see physicists become useful again. And I hope we're going to see that within the next months and years. But I totally agree with you. And like theoretical physicists, if you want to do something in the real world, we're not very useful. But we can be useful in telling engineers there is a new thing you can do, and this is the intelligent way to do it. And that hasn't happened in a deep fundamental foundation of physics way in 100 years, maybe, right? We've gone into the depths of quantum mechanics, but we've not gone a step further. But I think we might be there. We might be actually doing a step beyond.
Yeah, well, you know, when you show up, we'll talk physics. I'll show you what's on the stupid whiteboard from, I don't know, a year or two ago. It's all Charlie's squiggles. I'm sure they mean something. I just don't know what they are. But I just really, you know, I love listening to Curtis and Dave Chester, I think, and yourself and all these other guys with all these other theories, and you know, I made it all the way up to vector field theory, and you know, I did pretty good, and I was an aerospace guy, but all these squiggles don't mean nothing to me, because y'all just invent new squiggles. You know, you show me which thing to do to what to double my thrust, I'll be super impressed.
I'm gonna try that. Yeah.
Okay.
And I'm quite sure that Curtis is going to beat me to it, but I'm going to try it from a Heim perspective. I'm working on it, and we are chatting on it, and yeah, let's see. I'm going to try my best, and I really hope that I can give you some intelligent ideas how to better your setup. Yeah, but
awesome.
Let's see if I actually can.
So.
Okay. Well, I guess Tim's not going to turn off the recorder, so I'm going to cut out. Jared, I'll send you an email.
Yep, I just wanted to plug out there in the other chat there. I put the same link there.
Yeah, well, guys, it is the top of the hour. It's just about 6 p.m. Pacific. So why don't I close things out for today, and then so you don't need to bug out, but. Why don't I do that? So I'll end the stream here. This has been APEC for Saturday, April 11th, 2026. I would say overall, this is probably one of our best conference presentations ever. And thank you, Mikolaj, and thank you, Joel and Jared and Drew. I mean, and thank you to everybody who presented today. This was absolutely amazing.
Thank you, Tim.